The night sky has always been humanity's first teacher, our oldest mystery and our most enduring obsession. Imagine standing in a desert far from city lights, where the Milky Way stretches across the heavens like a river of diamonds. Each pinprick of light represents a sun, perhaps with its own family of planets, maybe even harboring life looking back at us with the same wonder. But what you see is an illusion, a beautiful lie told by the speed of light. The stars you're gazing at aren't where they appear to be. Some have already died, their light only now reaching your eyes after traveling for thousands of years. You're not looking at the universe as it is, but as it was. You're a time traveler, witnessing the past, standing in the present, unable to see the now of anything beyond our immediate cosmic neighborhood. This is where our journey begins, with a fundamental realization that the universe is far stranger, far more mysterious, and far more wonderful than our ancestors ever imagined. The ancient observers. 5,000 years ago, Babylonian priests climbed ziggurats to chart the movements of celestial bodies. They noticed patterns, the moon's phases, the wandering of planets, the annual return of constellations. They believed the heavens were a divine clockwork, messages from the gods written in light. They were wrong about the gods, but right about one thing: the universe follows patterns, laws that can be understood. The ancient Greeks took this further. Aristotle proposed that the earth sat at the center of a series of crystalline spheres, each carrying a celestial body in perfect circular motion. It was elegant, intuitive, and completely incorrect. Yet, it dominated Western thought for nearly 2,000 years. Then came the revolutionaries. Copernicus whispered that perhaps Earth wasn't the center of everything. Galileo pointed his primitive telescope skyward and saw moons orbiting Jupiter, proof that not everything revolved around us. Kepler discovered that planetary orbits were ellipses, not circles, shattering the ancient assumption of celestial perfection. Newton unified heaven and earth with his law of universal gravitation, showing that the same force that makes an apple fall also keeps the moon in orbit. For the first time, humanity had a mathematical framework that could predict the motions of the cosmos. The universe, it seemed, was becoming less mysterious, or so they thought. The 20th century, when everything changed. The year 1905 should be marked in history as the year humanity's understanding of reality fundamentally shifted. A young patent clerk named Albert Einstein published 4 papers that would revolutionize physics. One of them introduced special relativity, revealing that space and time weren't separate, absolute things, but were interwoven into a 4-dimensional fabric that could bend, stretch, and warp. Time, Einstein showed, wasn't universal. 2 observers moving at different speeds would experience time differently. Travel fast enough, and you could journey into the future. The faster you move through space, the slower you move through time. This wasn't philosophy or speculation, it was mathematics, and it made predictions that were tested and confirmed again and again. 10 years later, Einstein went further with general relativity, showing that gravity wasn't a force in the traditional sense, but the curvature of space-time itself. Massive objects like stars and planets create dips in the fabric of space-time, and other objects roll toward them like marbles on a stretched rubber sheet. This theory predicted things that seemed impossible, that light could be bent by gravity, that time runs slower near massive objects, that the universe itself might be expanding or contracting, and that there could exist objects so dense that nothing, not even light, could escape their gravitational pull. Black holes. The term wouldn't be coined until 1967, but Einstein's equations had predicted them in 1915. The expanding universe. In the 1920s, an astronomer named Edwin Hubble made an observation that would change everything. Using the most powerful telescope of his time, he measured the light from distant galaxies and noticed something peculiar. The light was shifted toward the red end of the spectrum. This redshift meant the galaxies were moving away from us, and the farther away they were, the faster they were receding. The universe was expanding. This wasn't an explosion moving through space, it was space itself expanding, carrying galaxies along with it like raisins in rising bread dough. If the universe was expanding, that meant it must have been smaller in the past. Trace it back far enough, and you arrive at a moment when all of space, time, matter, and energy were compressed into an infinitesimally small point. The Big Bang. Approximately 13.8 billion years ago, the universe began, not as an explosion in space, but as an explosion of space itself. In the first fraction of a second, the universe expanded faster than the speed of light, which is allowed because it's space itself expanding, not objects moving through space. In those first moments, the fundamental forces separated, particles formed, and the seeds of all future structure were planted. Within minutes, the first atomic nuclei formed. Within 380,000 years, the universe cooled enough for atoms to form, and light could finally travel freely through space. That light, stretched and cooled by billions of years of expansion, still fills the universe today as the cosmic microwave background radiation, a faint glow visible in every direction, the afterglow of creation itself. We've detected it. We've mapped it. It's real. The Big Bang theory has been confirmed by multiple independent lines of evidence. It's as close to certain as science gets, and yet it raises more questions than it answers. Nuritron. The questions that haunt us. What came before the Big Bang? The question itself might be meaningless. If time itself began with the Big Bang, then before doesn't exist. It's like asking what's north of the North Pole. But our minds rebel against this. Surely something must have caused the Big Bang. Surely there must be a deeper explanation, and that's just the beginning of the mysteries. Why does the universe have the laws of physics it has? Why is the speed of light exactly 299,792,458 meters per second? Why does gravity have the strength it does? Why are there 4 fundamental forces instead of 3 or 5? The values of the fundamental constants of nature appear to be finely tuned for the existence of complex structures like stars, planets, and life. Change any of them by even a tiny amount, and the universe would be radically different, perhaps just a thin soup of particles, or a universe that collapsed back on itself moments after the Big Bang, or one where atoms could never form. Is this fine-tuning evidence of design? Of a multiverse where every possible combination exists, and we simply find ourselves in one that allows observers? Or is there a deeper theory we haven't discovered yet that explains why these values must be what they are? We don't know. The visible and the invisible. Here's something that should disturb you. Everything we can see, every star, every galaxy, every nebula, every planet, all of it makes up less than 5% of the universe. Let me repeat that. The entire visible universe, everything that emits or reflects light, everything made of atoms, constitutes less than 5% of what exists. So what's the other 95%? About 27% is something we call dark matter. We can't see it, we can't detect it directly, but we know it's there because of its gravitational effects. Galaxies rotate too fast to be held together by the gravity of their visible matter alone. They should fly apart, but they don't. Galaxy clusters bend light from more distant objects far more than their visible mass can account for. Something invisible is providing additional gravity. Dark matter doesn't interact with light at all. It passes through ordinary matter like a ghost. It could be streaming through you right now, billions of particles every second, and you'd never know it. We've built detectors deep underground, shielded from cosmic rays, waiting to catch the rare interaction of a dark matter particle with ordinary matter. So far, we've found nothing conclusive. We know dark matter exists. We can map its distribution across the universe. But we have no idea what it actually is. And then there's the remaining 68%, dark energy. This is even stranger. The accelerating cosmos. In 1998, 2 teams of astronomers were studying distant supernovae, exploding stars that serve as cosmic distance markers. They expected to find that the expansion of the universe was slowing down, pulled back by the gravity of all the matter it contains. Instead, they found the opposite. The expansion is accelerating. Something is pushing the universe apart, overcoming gravity, causing galaxies to rush away from each other at ever-increasing speeds. We call this mysterious force dark energy, but that's just a label for our ignorance. Dark energy appears to be a property of space itself. As the universe expands and more space comes into existence, there's more dark energy, which accelerates the expansion further, creating more space and so on. If this continues, and we have no reason to think it won't, the universe will expand forever, growing colder and more dilute. Eventually, billions of years from now, galaxies beyond our local group will recede so far and so fast that their light will never reach us. The universe will appear to be emptying out, with only our local cluster of galaxies visible, surrounded by an ever-growing void. Trillions of years in the future, intelligent beings might look at the sky and see only their own galaxy, with no evidence that anything else exists. They would have no way to discover the Big Bang, no cosmic microwave background to detect, no distant galaxies to observe. They would be cosmologically isolated, unable to discover the true nature of the universe. We're lucky to live in an era when the universe is still revealing its secrets, but we're also unlucky because we've discovered that most of the universe is made of things we don't understand. The quantum realm. As if the mysteries of the cosmos weren't enough, the universe gets even stranger when you look at the very small. Quantum mechanics, the physics of atoms and subatomic particles, reveals a reality that defies common sense. Particles can be in multiple places at once until observed. They can tunnel through barriers that should be impenetrable. They can be entangled with each other across vast distances, instantaneously affecting each other in ways that Einstein called spooky action at a distance. An electron isn't a tiny ball orbiting a nucleus like a planet around a sun. It's a cloud of probability, existing everywhere in its orbital at once until something measures its position, at which point the wave function collapses and the electron appears in one specific location. But here's the disturbing part. We don't know what constitutes a measurement or why observation causes the wave function to collapse. Is consciousness required? Does the universe split into multiple branches, with each possible outcome occurring in a different reality? Is there an objective collapse mechanism we haven't discovered? These aren't just philosophical questions, they're fundamental gaps in our understanding of reality. The equations of quantum mechanics are the most precisely tested in all of science. They've been confirmed to extraordinary accuracy. Every piece of modern technology, from smartphones to solar panels to MRI machines, relies on quantum mechanics. And yet, we don't really understand what it means. Mirror, the paradox of Oso, knowledge. Here's the central paradox of modern science. The more we learn, the more we realize how much we don't know. Ancient humans had simple explanations for everything. Thunder was the anger of gods. Disease was caused by evil spirits. The stars were holes in the celestial sphere. They were wrong, but they felt certain. We've replaced those simple stories with mathematics and observation, with theories that make testable predictions and technologies that work. We've sent robots to Mars, detected gravitational waves from colliding black holes, and photographed the shadow of a black hole's event horizon. We've accomplished miracles. And yet, we can't explain what most of the universe is made of. We can't reconcile quantum mechanics with general relativity. We don't know if the universe is finite or infinite. We don't know if we're alone in the cosmos or if life is common. We don't know if there are other universes beyond our own. We don't even know if the laws of physics are the same everywhere, or if they might vary in distant regions of space or different epochs of time. The universe has revealed itself to be far more mysterious than our ancestors imagined. They thought the sky was a dome with holes for starlight. We know it's an expanding space-time containing hundreds of billions of galaxies, each with hundreds of billions of stars, stretching across billions of light years. But with that knowledge comes humility. The human perspective. There's something profound about our position in the cosmos. We're made of atoms forged in the hearts of dying stars. We're standing on a rocky planet orbiting an average star in an unremarkable galaxy in an ordinary part of the universe. We're insignificant. And yet, we're also extraordinary. We're the universe becoming conscious of itself. We're atoms arranged in such a way that we can contemplate our own existence, study our origins, and ask questions about our ultimate fate. In the entire observable universe, a sphere 93 billion light-years across containing perhaps 2 trillion galaxies, we know of only one place where matter has organized itself into structures capable of understanding quantum mechanics, general relativity, and the Big Bang. Maybe life is common, and we simply haven't found it yet. Maybe intelligence is rare, and we're one of the few species to ever ask these questions. Either answer is profound. If we're alone, then we're the universe's only hope of understanding itself. If we're not alone, then somewhere out there, other beings are looking at their sky, asking the same questions, feeling the same wonder. The journey ahead. This script is a journey through the greatest mysteries of existence. We'll explore the invisible scaffolding of dark matter that holds galaxies together. We'll confront the enigma of dark energy tearing the universe apart. We'll venture to the edge of black holes where space and time break down. We'll ask why, in a universe billions of years old and trillions of light years across, we haven't encountered any other intelligent civilizations. We'll dive into the quantum realm, where particles exist in superposition and reality itself seems to depend on observation. We'll consider the possibility of a multiverse, infinite parallel realities where every possible outcome occurs. We'll grapple with the nature of time, that mysterious dimension that flows in only one direction, and ask whether the past and future are as real as the present. We'll trace the universe from its fiery birth to its ultimate fate, whether that's a big freeze, a big rip, or something we haven't imagined yet. And through it all, we'll maintain a sense of wonder. Because that's what separates science from mere facts. Science isn't just about knowing, it's about the joy of discovery, the thrill of understanding something new, the humility of realizing how much remains unknown. The universe doesn't owe us answers. It doesn't care if we understand it or not. The fact that we can understand it, even partially, is a gift. The method of discovery. Before we dive into specific mysteries, it's worth understanding how we know what we know. Science isn't about certainty, it's about evidence, testing, and the willingness to be wrong. A scientific theory isn't a guess. It's a comprehensive explanation supported by vast amounts of evidence, making testable predictions that can be verified or falsified. Gravity is a theory. Evolution is a theory. The Big Bang is a theory. That doesn't make them uncertain. It makes them the best explanations we have, supported by everything we've observed. When new evidence contradicts a theory, the theory must change or be discarded. This isn't a weakness. It's science's greatest strength. Newton's laws of motion worked perfectly for centuries, accurately predicting the movements of planets and projectiles. Then we discovered they break down at very high speeds and in very strong gravitational fields. Einstein's relativity replaced Newton's laws in these extreme conditions, but Newton's laws still work perfectly for everyday situations. Science builds on itself, refining and extending our understanding. The mysteries we'll explore aren't failures of science, they're the frontier, the edge of human knowledge where the next great discoveries await. Some of these mysteries might be solved in our lifetimes. We might detect dark matter particles, develop a theory of quantum gravity, or discover life on another world. Other mysteries might remain unsolved for centuries or forever. And that's okay. The pursuit of knowledge is valuable in itself, regardless of whether we reach final answers. Nadur an invitation. This script is an invitation to wonder. You don't need a PhD in physics to appreciate these mysteries. You don't need to understand the mathematics, though we'll touch on it where relevant. You just need curiosity and a willingness to have your mind expanded. Some of what you'll read will challenge your intuitions. The universe doesn't care about what seems reasonable to creatures who evolved on an African savanna. Reality operates according to its own rules, and those rules are often strange. But strange doesn't mean incomprehensible. With patience and imagination, we can grasp these concepts. We can understand, at least in broad strokes, what dark matter is and why we think it exists. We can comprehend how black holes warp spacetime and what happens at their event horizons. We can follow the logic of the Fermi Paradox and consider its implications. We can become cosmic citizens, aware of our place in the vast tapestry of existence. Gershon. The promise. I promise you this. By the end of this journey, you'll never look at the night sky the same way again. You'll know that the darkness between stars isn't empty, but filled with invisible dark matter and dark energy. You'll understand that black holes aren't cosmic vacuum cleaners, but regions where space-time curves so severely that it creates a one-way boundary in reality. You'll appreciate that every atom in your body was forged in the heart of a star that died before our sun was born. You'll grasp that the universe is not only stranger than we imagine, but stranger than we can imagine. And yet, we keep imagining, keep discovering, keep pushing the boundaries of knowledge. This is humanity's greatest adventure, the quest to understand the cosmos and our place within it. So let's begin. Let's explore the unexplained mysteries of the universe, not with fear or superstition, but with wonder, curiosity, and the tools of science. The universe is waiting. In 1933, a Swiss astronomer named Fritz Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies located about 320 million light-years from Earth. He was measuring how fast these galaxies were moving, expecting to find velocities consistent with the cluster's visible mass. What he found made no sense. The galaxies were moving far too fast. According to Newton's laws and Einstein's relativity, they should have been flung apart long ago, scattered across the cosmos like sparks from a firework. The visible matter in the cluster, all those stars, all that gas and dust, didn't have nearly enough gravitational pull to hold everything together. Zwicky proposed a radical solution. There must be invisible matter, far more of it than visible matter, providing the additional gravity needed to keep the cluster bound. He called it dunkle materie, dark matter. Most astronomers ignored him. Zwicky was known for brilliant insights, but also for controversial ideas. Surely there was a simpler explanation. Maybe his measurements were wrong. Maybe our understanding of gravity needed a small adjustment. Decades passed. The evidence kept accumulating. The rotation problem. In the 1970s, astronomer Vera Rubin was studying spiral galaxies, measuring how fast stars orbit around their galactic centers. She expected to find that stars farther from the center would orbit more slowly, just as outer planets in our solar system orbit more slowly than inner planets. That's how gravity works. The farther you are from the mass, the weaker its pull, and the slower you need to move to maintain orbit. But that's not what Rubin found. Stars at the outer edges of galaxies were moving just as fast as stars closer to the center. The rotation curves were flat, not declining. This violated everything we knew about orbital mechanics. There were only two possible explanations. Either our understanding of gravity was fundamentally wrong, or there was additional invisible mass distributed throughout and around galaxies, providing extra gravitational pull. Rubin's work was meticulous and undeniable. Other astronomers confirmed her findings in galaxy after galaxy. The evidence was overwhelming. Something invisible was out there, and there was a lot of it. What dark matter isn't? Before we discuss what dark matter might be, let's clarify what it isn't. It's not ordinary matter that's simply dark, like planets, black holes, or clouds of cold gas. We call ordinary matter baryonic matter because it's made of baryons, protons, and neutrons. We can detect baryonic matter in many ways. It absorbs light, emits radiation, heats up, cools down, and interacts electromagnetically. We've looked for dark baryonic matter. We've searched for massive compact halo objects, MACOs, things like brown dwarfs, neutron stars, or black holes that could be lurking in the halos of galaxies. We've found some, but nowhere near enough to account for the missing mass. Dark matter also isn't antimatter. Antimatter annihilates when it contacts regular matter, producing gamma rays. We'd see the signature of these annihilations if there were large amounts of antimatter in galaxies. It's not black holes, at least not conventional ones. Black holes bend light through gravitational lensing, and we detect their presence. Plus, the formation of enough black holes to account for dark matter would have left other observable signatures in the early universe. So, what is it? Virchow, the leading candidates. The most popular hypothesis is that dark matter consists of exotic particles that don't interact with electromagnetic radiation. They don't emit, absorb, or reflect light. They only interact through gravity and possibly the weak nuclear force. These hypothetical particles are called WIMPs, weakly interacting massive particles. WIMPs would have been created in the first moments after the Big Bang, when the universe was a seething soup of energy and particles. As the universe expanded and cooled, these particles would have survived, spreading throughout space, clustering around galaxies due to gravity. They'd be passing through you right now, billions of them every second, without you ever noticing. They'd pass through the Earth, through the Sun, through everything, only rarely interacting with ordinary matter. Scientists have built incredibly sensitive detectors deep underground, shielded from cosmic rays and other interference, hoping to catch the rare moment when a WIMP collides with an atomic nucleus. These detectors are cooled to near absolute zero and monitored for the tiniest energy deposits. So far, despite decades of searching, we haven't found definitive evidence of WIMPs. This doesn't mean they don't exist. They might just interact even more weakly than we thought. But it's led scientists to consider alternatives. Another candidate is the axion, a hypothetical particle much lighter than a WIMP. Axions were originally proposed to solve a different problem in particle physics, but they could also account for dark matter. They'd be produced in enormous quantities in the early universe and would behave like a wave permeating space. Experiments are underway to detect axions using powerful magnetic fields to convert them into detectable photons. Then, there are more exotic possibilities: sterile neutrinos, dark photons, or even primordial black holes formed in the first fraction of a second after the Big Bang. We're searching for all of them. Gravitational evidence. While we haven't detected dark matter particles directly, we have overwhelming indirect evidence of dark matter's existence through its gravitational effects. Gravitational lensing. When light from a distant galaxy passes near a massive object, the object's gravity bends the light's path, creating distorted or multiple images of the background galaxy. By studying these distortions, we can map the distribution of mass, including dark matter. The results are stunning. We can create maps showing where dark matter is concentrated, and it doesn't always align with visible matter. In some galaxy clusters, collisions have separated the dark matter from the ordinary matter, providing direct evidence that they're distinct substances. The Bullet cluster is the most famous example. Two galaxy clusters collided, and the hot gas, ordinary matter, slowed down due to electromagnetic interactions, while the dark matter passed right through, continuing onward. Gravitational lensing reveals that most of the mass is in the dark matter, not the visible gas. This is powerful evidence that dark matter isn't just a modification of gravity, it's actual stuff with mass and location. Cosmic microwave background. The CMB, that afterglow of the Big Bang, contains tiny temperature fluctuations that reveal the density variations in the early universe. The pattern of these fluctuations depends on the ratio of ordinary matter to dark matter. The data fits perfectly with a universe that's about 27% dark matter and only 5% ordinary matter. Large-scale structure. The distribution of galaxies across the universe, the formation of galaxy clusters, and the cosmic web of filaments connecting them, all of this structure formed because dark matter's gravity pulled ordinary matter together. Computer simulations that include dark matter produce a universe that looks like ours. Simulations without dark matter produce a universe that looks nothing like what we observe. The dark matter halo. Every galaxy, including our Milky Way, is embedded in a vast halo of dark matter, extending far beyond the visible stars. This halo is roughly spherical and contains about 10 times more mass than all the stars, gas, and dust in the galaxy combined. It's the gravitational scaffolding that allowed the galaxy to form in the first place. In the early universe, dark matter began clumping together first because it doesn't interact electromagnetically and thus wasn't affected by radiation pressure. These dark matter clumps created gravitational wells, and ordinary matter fell into them, eventually forming stars and galaxies. Without dark matter, galaxies as we know them couldn't exist. The Milky Way's dark matter halo extends perhaps 600,000 light-years from the galactic center, far beyond the visible disk of stars, which is only about 100,000 light-years across. You're inside this halo right now. Dark matter particles are streaming through you, through the Earth, through everything, completely unnoticed. Or modified gravity theories. Not everyone accepts that dark matter exists. Some physicists propose that instead of invisible matter, we need to modify our theory of gravity. The most well-known alternative is MOND, Modified Newtonian Dynamics. MOND proposes that gravity behaves differently at very low accelerations, like those experienced by stars in the outer regions of galaxies. With this modification, you don't need dark matter to explain galaxy rotation curves. MOND works surprisingly well for individual galaxies, but it struggles to explain galaxy clusters, gravitational lensing, and the cosmic microwave background. It also lacks a relativistic formulation that's compatible with Einstein's general relativity. Other modified gravity theories have been proposed, each trying to explain the observations without invoking dark matter. Some are quite sophisticated, incorporating ideas from string theory or extra dimensions, but none of them explain all the observations as well as dark matter does. The scientific consensus is that dark matter exists, though the exact nature of the particles remains unknown. The search continues. The hunt for dark matter is one of the most intensive efforts in modern physics, pursued through three complementary approaches. Direct detection. Building ultra-sensitive detectors to catch dark matter particles interacting with ordinary matter. These experiments are conducted deep underground to shield them from cosmic rays. The detectors use various target materials, xenon, germanium, argon, and different detection methods. Experiments like Xenon 1T, LUX, and Panda-X have set increasingly stringent limits on WIMP properties, but haven't yet made a definitive detection. Indirect detection. Looking for the products of dark matter particle annihilations or decays. When two dark matter particles collide, they might annihilate, producing gamma rays, neutrinos, or other particles we can detect. Space-based telescopes like Fermi and ground-based observatories are searching for excess gamma rays from regions with high dark matter density, like the galactic center or nearby dwarf galaxies. Some anomalies have been found, but none have been conclusively attributed to dark matter. Collider production. Creating dark matter particles in particle accelerators like the Large Hadron Collider. If dark matter particles can be produced in high-energy collisions, they'd escape the detector without leaving a trace, but we'd notice missing energy and momentum. The LHC has searched for such signatures and found nothing conclusive, which has ruled out certain types of WIMPs. The implications. The existence of dark matter has profound implications for our understanding of the universe. First, it means that the matter we're made of, atoms, molecules, everything we can touch and see, is a minority component of the universe. We're not just physically small compared to the cosmos, we're made of the rare stuff. Second, it suggests that there's an entire sector of physics we haven't discovered yet. Dark matter particles would be part of a dark sector that might include dark forces and dark interactions we know nothing about. There could be a rich complexity to the dark sector, just as there is to the ordinary sector with its atoms, molecules, chemistry, and biology. We don't know if dark matter can form complex structures, but it's possible. Third, dark matter played a crucial role in the formation of all cosmic structure. Without it, the universe would be a very different place, perhaps just a thin uniform soup of hydrogen and helium, with no galaxies, no stars, no planets, and no us. the frustration and the hope. For physicists, dark matter is both frustrating and exciting. Frustrating because we've been searching for decades without a definitive detection. Every null result narrows the possibilities, but doesn't give us the answer. Exciting because we know there's something out there to find. This isn't a speculative hypothesis. Dark matter's gravitational effects are real and measurable. We're not chasing a phantom, we're hunting something that definitely exists. The discovery of dark matter particles would be one of the greatest scientific achievements in history, opening up an entirely new field of physics. It might happen tomorrow, or it might take another 50 years. But somewhere in the universe, dark matter particles are waiting to be found. Living in a dark universe. There's something humbling about dark matter. For all our scientific progress, for all our technological achievements, we still don't know what most of the matter in the universe is made of. We've mapped the human genome, landed robots on Mars, and detected gravitational waves from colliding black holes. We've built machines that can simulate the first moments after the Big Bang and telescopes that can see nearly to the edge of the observable universe. And yet, 27% of the universe is made of something we can't identify. This isn't a failure. It's a reminder that nature is under no obligation to make itself easy to understand. The universe operates according to its own rules, and those rules don't care about human intuition or convenience. Dark matter doesn't glow, doesn't emit radiation, doesn't interact electromagnetically. It's invisible, not because it's hiding, but because that's simply its nature. To detect it, we have to be clever. We have to build detectors more sensitive than anything that's come before. We have to think creatively about what dark matter might be and how it might reveal itself. This is science at its best, confronting a genuine mystery, gathering evidence, testing hypotheses, and slowly narrowing down the possibilities. The next chapter. Dark matter is just one piece of the cosmic puzzle. It explains why galaxies hold together and how large-scale structure formed, but it doesn't explain everything. In particular, it doesn't explain why the universe's expansion is accelerating. For that, we need something even stranger: dark energy. If dark matter is mysterious, dark energy is downright baffling. It's not a particle or a field in the traditional sense. It's a property of space itself, and it makes up 68% of the universe. Together, dark matter and dark energy account for 95% of the universe's content. Everything we can see, everything we're made of, is just the 5% left over. We live in a universe dominated by things we don't understand. And that's where our journey continues. October 1998. Two independent teams of astronomers announced results that would earn them the Nobel Prize and fundamentally alter our understanding of the universe's fate. They had been studying Type Ia supernovae, exploding white dwarf stars that serve as standard candles, because they all have roughly the same intrinsic brightness. By comparing how bright they appear to how bright they should be, astronomers can calculate their distance with remarkable precision. Both teams, the Supernova Cosmology Project led by Saul Perlmutter and the High-Z Supernova Search Team led by Brian Schmidt and Adam Rees, were using these cosmic explosions to measure how the universe's expansion rate has changed over time. Everyone expected the expansion to be slowing down. Gravity, after all, pulls everything together. The Big Bang had set the universe expanding, but gravity should be gradually putting on the brakes. The data said otherwise. Distant supernovae were dimmer than expected, meaning they were farther away than they should be if the expansion were slowing. The universe wasn't just expanding, it was accelerating. Something was pushing the universe apart, overcoming gravity, causing galaxies to rush away from each other faster and faster. The discovery was so unexpected that both teams spent months checking and rechecking their data, looking for errors. There had to be a mistake. The universe couldn't be accelerating, but the data was solid. The universe is accelerating, driven by something we call dark energy. Einstein's greatest blunder. That wasn't. Ironically, Einstein had predicted something like dark energy decades earlier, then abandoned it as his greatest blunder. In 1917, when Einstein applied his newly developed general relativity to the entire universe, he encountered a problem. His equations predicted that the universe should be either expanding or contracting. It couldn't remain static. But in 1917, everyone believed the universe was eternal and unchanging. The idea of a dynamic universe seemed absurd. To make his equations produce a static universe, Einstein added a term he called the cosmological constant, represented by the Greek letter lambda, L. This constant represented a repulsive force inherent to space itself, perfectly balanced against gravity to keep the universe static. It was an ad hoc addition, mathematically allowed but physically unmotivated. Then Hubble discovered that the universe was expanding. Einstein realized he didn't need the cosmological constant. The universe wasn't static after all. He reportedly called it his greatest blunder and removed it from his equations. But now, 80 years later, the cosmological constant was back. Dark energy behaves exactly like Einstein's cosmological constant, a property of space itself that doesn't dilute as the universe expands. As space grows, there's more dark energy, which accelerates the expansion further, creating more space and so on. Einstein's blunder might have been one of his greatest insights. What is dark energy? Here's the honest answer. We don't know. We can describe what it does. It accelerates the expansion of the universe. We can measure how much of it there is, about 68% of the universe's total energy density. We can observe its effects on cosmic evolution, but we don't know what it fundamentally is. The simplest explanation is that dark energy is the cosmological constant, a fixed energy density inherent to space itself. Every cubic meter of space contains the same amount of dark energy now and forever. This has a strange implication. As the universe expands and space increases, the total amount of dark energy increases. Energy is being created out of nothing, violating what we thought was a fundamental law, conservation of energy. Except in general relativity, energy conservation isn't quite as straightforward as in classical physics. In an expanding universe, energy doesn't have to be conserved globally. It's weird, but it's allowed by the equations. If dark energy is the cosmological constant, it raises a profound question. Why does it have the value it does? Quantum field theory predicts that empty space should have energy, the vacuum energy arising from quantum fluctuations. But when you calculate what this energy should be, you get a number that's 10 or 120 times larger than the observed dark energy density. That's not a typo. 10 to the power of 120. This is called the cosmological constant problem, and it's one of the worst predictions in the history of physics. Something is canceling out almost all of the vacuum energy, leaving just a tiny residual amount that we observe as dark energy. We have no idea what or why. Alternative explanations. Because the cosmological constant raises such difficult questions, physicists have proposed alternatives. Quintessence. Instead of a constant energy density, dark energy might be a dynamic field that changes over time and space. This field, called quintessence, would have been weaker in the early universe and has been growing stronger. Different quintessence models make different predictions about how dark energy's strength changes, which could potentially be tested with future observations. Modified gravity. Maybe there's no dark energy at all. Perhaps gravity behaves differently on cosmic scales than general relativity predicts. Various modified gravity theories have been proposed, each attempting to explain cosmic acceleration without invoking dark energy. The challenge is that general relativity has passed every test we've thrown at it, from the orbit of Mercury to gravitational waves. Any modification has to preserve all of relativity's successes while also explaining cosmic acceleration. Phantom energy. An even more exotic possibility is that dark energy's density is increasing over time. This would lead to a big rip scenario where the acceleration becomes so strong that it eventually tears apart galaxies, stars, planets, and even atoms. Current observations are consistent with a cosmological constant, but we can't yet rule out these alternatives. The fate of the universe. Dark energy determines the ultimate fate of the cosmos. If dark energy is a cosmological constant, the universe will expand forever, accelerating eternally. Galaxies beyond our local group will recede beyond our cosmic horizon, their light redshifted into oblivion. Star formation will eventually cease as galaxies run out of gas. Existing stars will burn out. The universe will grow darker and colder. In about 100 trillion years, the last stars will die. The universe will enter the degenerate era, dominated by stellar remnants, white dwarfs, neutron stars, and black holes. Even these won't last forever. Protons might decay given enough time. Black holes will evaporate through Hawking radiation, a process that takes 1,000 years for the largest black holes. Eventually, the universe will reach maximum entropy, a state of perfect uniformity and coldness where nothing interesting can ever happen again. This is called the heat death of the universe. It's a bleak picture, but it's trillions upon trillions of years away. If dark energy is phantom energy that grows stronger, the fate is more dramatic. The Big Rip would occur in perhaps 20 to 50 billion years. First, galaxy clusters would be torn apart, then galaxies, then solar systems, then planets, then atoms themselves. The universe would end not in cold darkness, but in violent disintegration. Current evidence favors the cosmological constant scenario, but we need more data to be certain. The coincidence problem. Here's something strange. Dark energy and matter have similar densities right now, in the current epoch of cosmic history. Dark energy makes up about 68% of the universe's energy density, while matter, dark and ordinary combined, makes up about 32%. But this ratio hasn't always been the same. In the early universe, matter dominated. Dark energy was there, but its density was negligible compared to matter's density. As the universe expanded, matter became more dilute. The same amount of matter spread over more space, but dark energy's density stayed constant, if it's a cosmological constant. Eventually, around 4 to 5 billion years ago, dark energy's density surpassed matter's density, and the universe's expansion began accelerating. Here's the coincidence. We happen to live in the brief cosmic epoch when these two densities are comparable. Before this era, matter dominated. After this era, in the far future, dark energy will dominate completely. Why do we find ourselves in this special time? This is called the coincidence problem, and it's deeply puzzling. One possible answer is the anthropic principle. We observe this epoch because it's the only epoch when observers like us can exist. Earlier, the universe was too young for complex life. Later, the accelerating expansion might prevent galaxy formation, making life impossible. We're here now because now is when life can exist. It's not a satisfying explanation to everyone, but it might be the correct one. Measuring the invisible. How do we study something we can't see or directly detect? We measure its effects on the universe's expansion history. Type Ia supernovae. These remain our best standard candles for measuring cosmic distances. By observing supernovae at different distances, and therefore different times in cosmic history, we can map how the expansion rate has changed. Baryon acoustic oscillations. In the early universe, sound waves propagated through the hot plasma, creating a characteristic scale in the distribution of matter. This scale is imprinted in the large-scale structure of galaxies and can be used as a standard ruler to measure cosmic expansion. Cosmic microwave background. The CMB contains information about the universe's geometry and composition. The pattern of temperature fluctuations depends on dark energy's properties. Weak gravitational lensing. Dark energy affects how cosmic structure grows over time. By measuring how light from distant galaxies is bent by intervening matter, we can track structure growth and infer dark energy's influence. All these methods point to the same conclusion. Dark energy exists and makes up about 68% of the universe. The vacuum catastrophe. Let's return to the cosmological constant problem, because it's truly one of the deepest mysteries in physics. Quantum mechanics tells us that empty space isn't really empty. Virtual particles constantly pop in and out of existence, borrowing energy from the vacuum for brief moments allowed by Heisenberg's uncertainty principle. This quantum vacuum should have energy, a lot of it. When physicists calculate this vacuum energy density, they get an absurdly large number. If it were real, the universe would have accelerated so rapidly that atoms could never have formed. Yet the observed dark energy density is 10 und 20 times smaller. Something is canceling out the vacuum energy to incredible precision, leaving just a tiny residual amount. We don't know what. Some physicists think this points to new physics, perhaps supersymmetry or extra dimensions, that naturally cancels the vacuum energy. But we haven't found evidence for these theories. Others think it's an anthropic selection effect. In a multiverse with different vacuum energies, only universes with small values allow life to exist, so we necessarily find ourselves in one of those rare universes. Still others think we're missing something fundamental about quantum field theory or general relativity. The cosmological constant problem remains unsolved. Dark energy and the multiverse. The multiverse hypothesis offers one possible explanation for dark energy's value. If there are countless universes, each with different physical constants and properties, then dark energy's value would vary from universe to universe. In most universes, dark energy would be either too large, preventing structure formation, or negative, causing the universe to recollapse quickly. Only in rare universes with just the right value could galaxies, stars, and life exist. We find ourselves in such a universe not because it's special, but because it's the only type where observers can exist to ask the question. This is the anthropic explanation, and it's controversial. Some physicists find it deeply unsatisfying. It seems to give up on finding a fundamental explanation. Others argue it might be the correct answer, even if it's not the answer we wanted. The multiverse hypothesis is difficult to test, which makes many scientists uncomfortable. Science relies on testable predictions, and if other universes are forever beyond our observation, can we ever confirm the hypothesis? Perhaps. Some multiverse models make predictions about patterns in the cosmic microwave background or other observable phenomena. The search continues. Bandar living in an accelerating universe. Dark energy's existence has practically implications for the far future. Galaxies beyond our local group are already receding from us, carried away by cosmic expansion. As dark energy accelerates this expansion, distant galaxies will eventually recede faster than light can travel through space. This doesn't violate relativity. Nothing is moving through space faster than light. Space itself is expanding, carrying galaxies with it. Once a galaxy crosses our cosmic horizon, its light will never reach us again. It effectively disappears from our observable universe. In about 100 billion years, all galaxies beyond our local group will have vanished beyond the horizon. Future astronomers will see only the Milky Way and its nearest neighbors, surrounded by darkness. They'll have no way to discover the Big Bang, no cosmic microwave background to detect, no distant galaxies to observe. They'll be cosmologically isolated. We're fortunate to live in an era when the universe still reveals its history. The ultimate mystery. Of all the mysteries we'll explore in this script, dark energy might be the most profound. Dark matter, at least, is matter, something with mass that clumps together. We don't know what particles it's made of, but we understand its general behavior. Dark energy is different. It's not particles, not fields in the usual sense. It's a property of space itself, or perhaps something even stranger. It dominates the universe's energy budget, determines the cosmos's ultimate fate, and yet we have no fundamental understanding of what it is. Every cubic meter of empty space contains dark energy. You're surrounded by it, immersed in it, and it's pushing the universe apart around you. And we have no idea why. This is the frontier of physics, the edge of human knowledge where the next great revolution awaits. Somewhere in the equations we haven't written yet, in the experiments we haven't performed, in the observations we haven't made, lies the answer. dark energy is waiting to reveal its secrets. Imagine compressing the Earth until it's the size of a marble, then compress it further until all its mass is contained in a space smaller than an atom. Keep compressing until you reach a point where the density becomes infinite and the laws of physics as we know them break down. You've just created a black hole. Black holes are regions of space-time where gravity is so intense that nothing, not matter, not light, not information, can escape once it crosses a boundary called the event horizon. They're not objects in the traditional sense, but rather extreme distortions in the fabric of reality itself. Einstein's general relativity predicted them in 1915, though Einstein himself didn't believe they could actually exist in nature. The mathematics was clear, but the implications seemed too bizarre. Then we found them. Not just one or two, but millions. There's likely a supermassive black hole at the center of every large galaxy, including our own. Stellar mass black holes are scattered throughout the galaxy, the remnants of massive stars that exhausted their fuel and collapsed. In April 2019, we even photographed one, or rather, we photographed its shadow, the dark silhouette it casts against the glowing matter swirling around it. Black holes are real, and they're among the strangest objects in the universe. The birth of a black hole. Most black holes form from the deaths of massive stars. When a star at least 20-25 times the mass of the Sun exhausts its nuclear fuel, there's nothing left to support it against gravity's crushing pull. The core collapses in less than a second, and the outer layers rebound in a catastrophic supernova explosion. If the core's mass exceeds about 3 solar masses, the Tolman-Oppenheimer-Volkoff limit, not even neutron degeneracy pressure can halt the collapse. The core continues shrinking, passing through the event horizon, and becomes a black hole. The entire process, from the start of core collapse to black hole formation, takes less than a second. From the outside, though, something strange happens. Due to gravitational time dilation, an outside observer watching matter fall toward the event horizon would see it slow down, redshift, and appear to freeze just at the horizon. The matter never seems to quite cross it. It just gets dimmer and dimmer, fading from view. But from the perspective of the falling matter, it crosses the horizon in finite time and continues falling toward the singularity at the center. This is one of the first hints that black holes do strange things to space and time. The event horizon. The event horizon is the defining feature of a black hole, the point of no return. It's not a physical surface. There's no wall, no barrier, nothing you could touch. It's simply the boundary where the escape velocity equals the speed of light. Outside the horizon, you could still escape if you had a powerful enough rocket. At the horizon, you'd need to travel at light speed to escape. Inside the horizon, escape would require traveling faster than light, which is impossible. The size of the event horizon depends on the black hole's mass. For a non-rotating black hole, the radius of the event horizon, called the Schwarzschild radius, is r-2gmc2, where g is the gravitational constant, m is the mass, and c is the speed of light. For a black hole with the mass of the Sun, the Schwarzschild radius is about 3 kilometers. For the supermassive black hole at the center of our galaxy, about 4 million solar masses, it's about 12 million kilometers, roughly 17 times the radius of the Sun. If you could somehow compress the Earth to the size of a marble, about 9 millimeters, it would become a black hole. Spaghettification. If you fell toward a black hole feet first, you'd experience something called tidal forces. Gravity decreases with distance, so your feet, closer to the black hole, would experience stronger gravity than your head. This difference would stretch you vertically while compressing you horizontally. For a stellar mass black hole, these tidal forces would become lethal long before you reach the event horizon. You'd be stretched like spaghetti, hence the term spaghettification, torn apart at the molecular level. For a supermassive black hole, though, the tidal forces at the event horizon are much weaker. You could cross the horizon intact, unaware that you'd passed the point of no return, but your fate would be sealed. Once inside, all paths lead to the singularity at the center, where you'd be crushed to infinite density in a finite amount of your time. What happens at the singularity? We don't know. Our theories break down there. General relativity predicts infinite curvature and density, which is a sign that the theory is incomplete. Most physicists believe that quantum effects become important at such extreme conditions, and a theory of quantum gravity would be needed to describe what really happens. We don't have such a theory yet. Rotating black holes. Real black holes aren't static. They rotate, often at tremendous speeds. A rotating black hole is described by the Kerr metric, discovered by Roy Kerr in 1963. And it's even stranger than a non-rotating one. The rotation drags space-time around with it in a phenomenon called frame dragging. Near the black hole, space itself is rotating, and anything in that region is forced to rotate along with it. There are actually two event horizons in a rotating black hole, an outer and an inner one. Between them is a region called the ergosphere, where you can't remain stationary. You're forced to rotate with the black hole, but you can still escape. Theoretically, you could extract energy from a rotating black hole through a process called the Penrose process, using the ergosphere to steal some of the black hole's rotational energy. At the center of a rotating black hole, the singularity isn't a point, it's a ring, and the mathematics suggests that this ring singularity might be a gateway to other regions of spacetime, perhaps even other universes. This is highly speculative, and most physicists think quantum effects would prevent such exotic possibilities. But the mathematics allows it, and that's intriguing. Hawking radiation. In 1974, Stephen Hawking made a stunning discovery. Black holes aren't completely black. Using quantum field theory and curved spacetime, Hawking showed that black holes emit radiation due to quantum effects near the event horizon. Here's a simplified explanation. Quantum mechanics allows particle-antiparticle pairs to spontaneously appear and annihilate. Near the event horizon, one particle might fall into the black hole while the other escapes. To an outside observer, it looks like the black hole is emitting radiation. This radiation carries away energy, which means the black hole loses mass. Over immense timescales, a black hole can completely evaporate for a stellar mass. Black hole. This process takes about 10^67 years, far longer than the current age of the universe, but smaller black holes evaporate faster. A black hole with the mass of a mountain would evaporate in about the age of the universe. As a black hole shrinks, it gets hotter and radiates faster, eventually exploding in a final burst of energy. Hawking radiation has never been directly observed. Black holes are too cold and the radiation too faint. But it's a robust prediction of combining quantum mechanics with general relativity. It also raises a profound puzzle: the information paradox. Tartiru, the information paradox. In quantum mechanics, information is never destroyed. If you know the exact quantum state of a system at one time, you can in principle calculate its state at any other time. But what happens to information that falls into a black hole? If the black hole eventually evaporates through Hawking radiation, and that radiation is purely thermal, containing no information about what fell in, then the information is lost. This violates quantum mechanics. Hawking originally argued that information is indeed destroyed, that black holes are an exception to quantum mechanics. This sparked decades of debate. Most physicists now believe that information is somehow preserved, encoded in subtle correlations in the Hawking radiation. But exactly how this works remains unclear. Some proposals involve the holographic principle, the idea that all the information about a volume of space can be encoded on its boundary. For a black hole, this would mean all the information is encoded on the event horizon. Others suggest that information escapes through quantum entanglement between particles inside and outside the horizon. The information paradox remains one of the deepest problems in theoretical physics, sitting at the intersection of quantum mechanics, general relativity, and thermodynamics. Supermassive black holes. At the center of most large galaxies lurks a supermassive black hole with masses ranging from millions to billions of times the mass of the Sun. Our galaxy's central black hole, Sagittarius AI, pronounced Sagittarius A star, has a mass of about 4 million suns. We've observed stars orbiting it at tremendous speeds, some completing an orbit in just 16 years. The black hole at the center of the M87 galaxy is the one we photographed in 2019. It has a mass of 6.5 billion suns and is shooting out a jet of matter at nearly the speed of light, extending for thousands of light years. How did these monsters form? We're not entirely sure. They're too massive to have formed from a single star. Possible formation mechanisms include collapse of massive gas clouds in the early universe, mergers of many smaller black holes, runaway collisions of stars in dense stellar clusters, direct collapse of regions in the early universe. Probably all these mechanisms played a role. Supermassive black holes are intimately connected to galaxy evolution. The energy they release as matter falls in can heat gas and regulate star formation. Galaxies and their central black holes seem to grow together, their masses correlated in ways we're still trying to understand. Quasars and active galactic nuclei. When matter falls toward a black hole, it doesn't fall straight in. It forms an accretion disk spiraling inward while heating up through friction. For a supermassive black hole, this accretion disk can outshine the entire galaxy, creating what we call a quasar or active galactic nucleus, AGN. Quasars are the most luminous objects in the universe. A single quasar can be brighter than 1 trillion stars, powered by a black hole consuming the equivalent of several Earths per hour. We see quasars mostly in the distant universe, meaning they were common when the universe was young. Today, most supermassive black holes are quiescent, having consumed most of the nearby matter. But they can reawaken. If a galaxy merger delivers fresh gas to the central black hole, it can flare back to life. In about 4 billion years, the Milky Way will collide with the Andromeda Galaxy. The two central black holes will eventually merge, possibly triggering a brief quasar phase before settling down again. Gravitational waves from black hole mergers. On September 14, 2015, the LIGO detectors in Louisiana and Washington state detected a signal that had traveled for 1.3 billion years. The gravitational waves from two black holes spiraling together and merging. This was the first direct detection of gravitational waves, confirming a century-old prediction of Einstein's general relativity. Since then, we've detected dozens of black hole mergers, along with neutron star mergers and even mixed black hole neutron star mergers. These observations have taught us that stellar mass black holes are more common and more massive than we expected. We've detected black holes up to 100 solar masses, larger than theoretical models predicted could form from stellar collapse. Perhaps they formed through mergers, or perhaps our understanding of stellar evolution needs revision. When black holes merge, they release enormous amounts of energy in gravitational waves, equivalent to several solar masses converted entirely to energy in a fraction of a second. The peak power output can exceed the combined light output of all stars in the observable universe, and we can detect it from Earth with lasers and mirrors. The shadow of a black hole. The 2019 image of the M87 black hole was a triumph of observational astronomy. To photograph something so small and distant required a telescope the size of Earth. This was achieved through very long baseline interferometry, VLBI, combining data from radio telescopes around the world. The image shows a bright ring of emission from the accretion disk with a dark shadow in the center, the black hole itself blocking light from behind it. The shadow is about 2.5 times larger than the event horizon, due to gravitational lensing bending light around the black hole. The image confirmed predictions from general relativity with remarkable precision. The size, shape, and brightness of the shadow all match theoretical expectations. In 2022, the Event Horizon Telescope team released an image of Sagittarius A's, our own galaxy's central black hole. It was more challenging to image because matter orbits it much faster, changing on timescales of minutes. These images are just the beginning. Future observations will test general relativity and the strong field regime, search for deviations that might hint at new physics, and perhaps even detect the photon ring, a series of increasingly faint rings created by light orbiting the black hole multiple times. Wormholes and time machines. The mathematics of general relativity allows for exotic solutions. wormholes connecting distant regions of space or even different universes. A wormhole would be a tunnel through space-time, potentially allowing faster-than-light travel, not through space, but through a shortcut in space-time itself. The problem is that wormholes, if they can exist at all, would be unstable and would collapse unless held open by exotic matter with negative energy density. We've never observed such matter, though quantum effects can produce negative energy densities in small regions, the Casimir effect. Even if wormholes could exist, using them for time travel raises paradoxes. Could you go back in time and prevent your own birth? Most physicists think such paradoxes mean that time travel to the past is impossible, or that the universe conspires to prevent paradoxes through quantum effects. But we don't know for sure. General relativity also allows for closed, time-like curves, paths through space-time that loop back on themselves, allowing time travel. These require extreme conditions, like infinitely long rotating cylinders or traversable wormholes. Whether nature actually permits such things remains an open question. The firewall paradox. Recent theoretical work has uncovered a new puzzle, the black hole firewall paradox. If information is preserved in Hawking radiation through quantum entanglement, then particles just outside the event horizon must be entangled with particles in the radiation that's already escaped. But quantum mechanics says a particle can only be maximally entangled with one other particle. If the particle outside the horizon is entangled with escaped radiation, it can't also be entangled with its partner inside the horizon. This suggests that the event horizon might not be empty space after all, but rather a firewall of high-energy particles that would incinerate anything trying to cross. But this contradicts the equivalence principle, the idea that free fall is indistinguishable from floating in empty space. Someone falling through the event horizon shouldn't notice anything special. We have three principles that seem incompatible. 1. Information is preserved, quantum mechanics. 2. The event horizon is smooth, equivalence principle. 3. Physics outside the horizon is normal, locality. Something has to give, but we don't know what. This is an active area of research, with proposals ranging from modifications to quantum mechanics to the idea that the interior of a black hole doesn't exist in the way we think. Living near a black hole. Could you orbit a black hole safely? Yes, as long as you stay outside the event horizon and avoid the accretion disk. The movie Interstellar depicted a planet orbiting close to a massive black hole, where time dilation was so extreme that 1 hour on the planet equaled 7 years elsewhere. This is theoretically possible for a rapidly rotating black hole, though the planet would need to orbit very close to the event horizon. The time dilation would be real. If you spent time near a black hole and then returned to Earth, you'd find that far more time had passed for everyone else. You'd have traveled to the future. Black holes are the ultimate time machines, for forward time travel, at least. The ultimate mystery. Black holes sit at the boundary of our knowledge, where general relativity and quantum mechanics meet and clash. They're real objects we can observe and study, yet they contain singularities where our theories break down. They challenge our understanding of information, causality, and the nature of space-time itself. Somewhere in the resolution of black hole paradoxes lies the key to quantum gravity, the theory that will unite Einstein's relativity with quantum mechanics. That theory might reveal that singularities don't actually exist, that they're replaced by something else at the quantum level. It might show that the event horizon is more complex than we thought, or that information escapes in ways we haven't imagined. Black holes are laboratories for extreme physics, testing our theories in conditions we can never reproduce on Earth, and they're waiting to teach us the next great lesson about the nature of reality. In the summer of 1950, physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory. The conversation turned to UFOs and the possibility of extraterrestrial life. Fermi suddenly asked, "Where is everybody?" It was a simple question with profound implications. The universe is 13.8 billion years old. Our galaxy alone contains 400 billion stars. Many of these stars have planets. The observable universe contains perhaps 2 trillion galaxies. Even if life is rare, even if intelligence is rarer still, even if technological civilizations are incredibly uncommon, the sheer numbers suggest there should be many advanced civilizations out there. Some should be millions or even billions of years older than us. They've had time to spread across the galaxy, to build megastructures, to leave unmistakable signs of their existence. So where are they? This is the Fermi Paradox, the apparent contradiction between the high probability of extraterrestrial civilizations and the complete lack of evidence for them. We've been listening for signals for over 60 years. We've found nothing. The silence is deafening. 3. The Drake equation. In 1961, astronomer Frank Drake formulated an equation to estimate the number of detectable civilizations in our galaxy. N. R x FPX NEX FLX FEX FCXL, where R shot rate of star formation, FP on fraction of stars with planets, and touched average number of habitable planets per star with planets, FLH fraction of habitable planets where life actually develops, Phi fraction of life-bearing planets where intelligence evolves, FC fraction of intelligent species that develop detectable technology, Yel'Radar's length of time such civilizations remain detectable. When Drake first wrote this equation, we knew almost none of these values. We had to guess. Today we know much more. We know that planets are common. Most stars have them. We know that many planets orbit in the habitable zone where liquid water can exist. But we still don't know FL, Phi, FC, or L. These are the great unknowns. Depending on what values you plug in, you can get answers ranging from "we're alone in the galaxy" to "there should be millions of civilizations." The fact that we haven't found any suggests that at least one of the terms is very small. But which one? Dartier. The Great Filter. The concept of the Great Filter, proposed by Robin Hanson, suggests that there's some step in the evolution from non-life to galaxy-spanning civilization that's extremely unlikely. This filter could be behind us or ahead of us. If it's behind us, then the hard step might be the origin of life itself, the development of complex cells, eukaryotes, the evolution of intelligence, the development of technology. If the Great Filter is behind us, we're extraordinarily lucky to have passed it. Life might be common, but intelligent, technological life is rare. We might be alone in the galaxy or even the observable universe. This is actually the optimistic scenario because it means we've already overcome the hardest challenge. If the Great Filter is ahead of us, that's terrifying. It would mean that something prevents civilizations from spreading across the galaxy. Perhaps they destroy themselves through war, environmental collapse, or technological catastrophe. Perhaps there's some inevitable disaster that befalls all advanced civilizations. If we discover simple life on Mars or Europa, that's bad news for the Great Filter hypothesis. It would suggest that life is common, which means the filter is more likely ahead of us. The more common we find life to be, the more worried we should be about our own future. Possible solutions to the paradox. Dozens of solutions have been proposed to the Fermi Paradox. Let's explore the most compelling. 1. We're alone, rare Earth hypothesis. Perhaps Earth is extraordinarily special. The conditions for complex life might require a star of the right type, not too hot, not too cool, a planet at the right distance, a large moon to stabilize the planet's tilt, Jupiter-sized planets to deflect asteroids, plate tectonics to recycle nutrients, a magnetic field to protect from radiation, the right atmospheric composition, billions of years of stability. Maybe all these factors together are so rare that intelligent life is unique to Earth, or at least extremely uncommon. 2. Intelligence is rare. Life might be common, but intelligence might be a rare accident. On Earth, life existed for 3.5 billion years before intelligence emerged. For most of Earth's history, the most complex life was bacteria. Multicellular life only appeared about 600 million years ago. Intelligence might not be an inevitable outcome of evolution. It might be a fluke, a random path that evolution rarely takes. 3. They're out there, but we can't detect them. Advanced civilizations might use communication technologies we can't detect. They might have moved beyond radio waves to quantum communication, neutrino beams, or methods we haven't imagined. We've only been listening for 60 years, and only to a tiny fraction of the sky at a limited range of frequencies. We might simply have missed them. 4. The zoo hypothesis. Perhaps advanced civilizations know about us but are deliberately avoiding contact, observing us like animals in a zoo. This seems anthropocentric and unfalsifiable, but it's possible. 5. They're here, but hidden. Maybe aliens are already on Earth, but we don't recognize them. Perhaps they exist as digital entities or in forms so different from biological life that we don't perceive them as alive. This seems unlikely, but we can't rule it out entirely. 6. Self-destruction is inevitable. Perhaps all technological civilizations eventually destroy themselves through nuclear war, climate change, artificial intelligence, nanotechnology, or some other catastrophe. If the typical lifetime of a technological civilization is only a few centuries, then at any given time, very few would exist. This is the darkest solution. It suggests our own future is grim. 7. The dark forest hypothesis. This idea, popularized by Liu Cixin's science fiction trilogy, suggests that the universe is like a dark forest where civilizations hide because revealing yourself is dangerous. If resources are limited and civilizations compete, it might be safer to remain silent and hidden. Any civilization that broadcasts its presence might be destroyed by others. This assumes a hostile universe, which seems pessimistic, but we can't know the motivations of alien civilizations. 8. They transcend. Perhaps sufficiently advanced civilizations lose interest in physical space. They might upload themselves into virtual realities, or transcend to higher dimensions, or achieve some post-physical existence. If the ultimate goal of intelligence is to understand the universe, perhaps advanced civilizations turn inward rather than outward. 9. The timing argument. The universe is 13.8 billion years old, but the first generations of stars contained almost no heavy elements. Planets like Earth, with rocky surfaces and complex chemistry, couldn't form until later generations of stars had created and dispersed heavy elements. Perhaps we're among the first technological civilizations to emerge. We're not late to the party, we're early. In a few billion years, the galaxy might be teeming with life. We just happen to be pioneers. The search for extraterrestrial intelligence, SETI. Since 1960, we've been actively searching for signals from extraterrestrial civilizations. The first search, Project Ozma, used a radio telescope to listen to 2 nearby stars for 150 hours. It found nothing. Since then, SETI has become more sophisticated. Modern searches scan millions of stars across wide frequency ranges, looking for narrow-band signals or other patterns that couldn't be natural. We've detected interesting signals. The famous WOW signal in 1977 was a strong, narrow-band signal that lasted 72 seconds and was never detected again. But we've never found anything conclusive. SETI also searches for optical signals, laser pulses that might be used for interstellar communication. And we look for technosignatures, evidence of large-scale engineering like Dyson spheres, megastructures that capture a star's energy, or waste heat from advanced civilizations. So far, nothing. The search continues with new telescopes and new strategies. The Breakthrough Listen project, funded by Yuri Milner, is the most comprehensive search ever, scanning millions of stars. If there's a signal out there, we're more likely to find it now than ever before. Messaging Extraterrestrial Intelligence, METI. Should we actively broadcast our presence? This is controversial. Some argue that we should send deliberate messages to nearby stars, increasing the chances of contact. Others, including Stephen Hawking, warned that this might be dangerous. We don't know how alien civilizations would react to discovering us. History shows that when a technologically advanced civilization encounters a less advanced one, it often ends badly for the latter. We've already sent a few messages, the Arecibo message in 1974, and messages attached to the Voyager and Pioneer spacecraft. But these are symbolic gestures. A serious METI-campaign would be much more powerful and persistent. The debate continues. Is the potential reward worth the risk? Biosignatures and technosignatures. We're not just listening for deliberate signals. We're also looking for indirect evidence of life and technology. Biosignatures are signs of life in a planet's atmosphere. Oxygen, for example, is highly reactive and wouldn't persist in Earth's atmosphere without constant replenishment by photosynthetic life. The James Webb Space Telescope and future missions will analyze the atmospheres of exoplanets, looking for combinations of gases that suggest biological activity. Technosignatures are signs of technology, industrial pollutants in an atmosphere, city lights on the night side of a planet, waste heat from energy consumption, large-scale engineering projects, artificial structures in orbit. We're developing the capability to detect these signs. Within a few decades, if there are technological civilizations on nearby exoplanets, we might find them. The implications of contact. What would happen if we detected a signal? First, we'd verify it obsessively. The signal would need to be confirmed by multiple independent observations before any announcement. Then, assuming it's real, we'd try to decode it. A deliberate signal would likely include information about the senders, their biology, their planet, their technology. The impact on humanity would be profound. Every religion, every philosophy, every understanding of our place in the universe would be challenged. We'd know we're not alone. We'd also know that the great filter, if it exists, can be overcome. At least one other civilization has survived long enough to send signals. This would be simultaneously reassuring and terrifying. The signal might contain warnings, advice, or knowledge far beyond our current understanding. Or it might be a simple greeting, a cosmic hello across the void. We might never get a reply to any message we send back. If the civilization is 1,000 light years away, a round-trip conversation would take 2,000 years, but we'd know, and that knowledge would change everything. The implications of silence. What if we search for centuries and find nothing? That would also be profound. It might mean we're alone, or nearly so. The responsibility of being the only intelligent life in the galaxy, perhaps the universe, would be staggering. It would mean that consciousness, art, science, love, and all the products of intelligence exist only here, on this small planet. If we destroy ourselves, we might be extinguishing the only light of consciousness in the cosmos. Alternatively, continued silence might mean the great filter is ahead of us. Other civilizations arose, developed technology, and then something happened. This should motivate us to be very careful with existential risks: nuclear weapons, climate change, artificial intelligence, biotechnology. We might be approaching the filter ourselves. Panspermia and the origin of life. One possible solution to the Fermi Paradox relates to the origin of life itself. Panspermia is the idea that life didn't originate on Earth, but was seeded from space, perhaps by comets or asteroids carrying microorganisms, or even deliberately by an advanced civilization. If panspermia is true, life might be common throughout the galaxy, all descended from a common origin. But this just pushes the question back. Where did that original life come from? We don't know how life began. We have hypotheses: chemical evolution in tidal pools, hydrothermal vents, clay surfaces, but no definitive answer. If the origin of life is extremely unlikely, that could be the great filter. Earth might be one of the few places where it happened, or life might be common, but intelligence is rare. We need more data. The future of the search. Our search for extraterrestrial intelligence is still in its infancy. We've examined a tiny fraction of the galaxy at a limited range of frequencies for a brief moment in cosmic time. It's like dipping a cup into the ocean and concluding there are no fish because you didn't catch any. The next generation of telescopes, the Square Kilometre Array, the Extremely Large Telescope, and others, will dramatically expand our search capabilities. We'll be able to detect weaker signals, scan more stars, and analyze more exoplanet atmospheres. Within our lifetimes, we might find evidence of life beyond Earth. It might be microbial life on Mars or Europa. It might be biosignatures in an exoplanet's atmosphere. It might be a technosignature or a deliberate signal, or we might find nothing, and the great silence will deepen. Either answer will reshape our understanding of our place in the universe. The cosmic perspective. The Fermi Paradox forces us to confront our cosmic significance, or insignificance. If we're alone, we're precious beyond measure. We're the universe's only way of knowing itself. If we're not alone, we're part of a galactic community, with all the opportunities and dangers that implies. Either way, the question, where is everybody, is one of the most important we can ask. The answer, whatever it is, will define humanity's future. Everything you think you know about reality is wrong. Not metaphorically wrong, not philosophically wrong, but fundamentally, demonstrably wrong. Objects can be in multiple places at once. Particles can communicate instantaneously across vast distances. The act of observation changes what you're observing. Reality itself seems to depend on measurement. This isn't philosophy or mysticism, it's quantum mechanics, the most precisely tested theory in the history of science. And it makes no sense, at least, it makes no sense according to our everyday intuitions. But the universe doesn't care about our intuitions. At the quantum level, reality operates according to rules that seem absurd, yet they're verified by every experiment we perform. Welcome to the quantum realm, where the impossible is routine and common sense is the first casualty. The double-slit experiment. Let's start with the experiment that reveals quantum weirdness in its purest form. Take a barrier with two narrow slits and shine light through it onto a screen. You'll see an interference pattern, alternating bright and dark bands, because light waves from the two slits overlap and either reinforce or cancel each other. This makes sense. Light is a wave and waves interfere. Now do the same experiment with electrons, firing them one at a time. Each electron is a particle. It should go through one slit or the other and hit the screen at a specific point. But that's not what happens. Even when you fire electrons one at a time, so that only one electron is in the apparatus at any moment, you still get an interference pattern. Each individual electron somehow interferes with itself, as if it went through both slits simultaneously. The electron behaves like a wave, not a particle. But here's where it gets truly strange. If you put a detector at the slits to see which one the electron goes through, the interference pattern disappears. The electron behaves like a particle again, going through one slit or the other. The act of measurement changes the outcome. This isn't a flaw in the experiment or a limitation of our technology. It's how reality works at the quantum level. Before measurement, the electron exists in a superposition. It's in multiple states simultaneously. Measurement forces it to choose one state. But what constitutes a measurement? Does it require a conscious observer? Does the universe split into multiple branches? Is there an objective collapse mechanism? We don't know. Wave-particle duality. Light behaves like a wave in some experiments and like a particle in others. So does matter. This is wave-particle duality, one of the central mysteries of quantum mechanics. It's not that light is sometimes a wave and sometimes a particle. It's that light and matter is something more fundamental that exhibits wave-like or particle-like behavior, depending on how you measure it. What is that fundamental thing? The mathematics describes it as a wave function, a mathematical object that encodes probabilities for different measurement outcomes. But what is the wave function? Is it a real physical wave propagating through space? Is it just a mathematical tool for calculating probabilities? Does it represent our knowledge about the system? These questions have been debated for a century, and there's still no consensus. Heisenberg's uncertainty principle. In classical physics, you can measure both the position and momentum of an object with arbitrary precision. In principle, if you knew the exact position and momentum of every particle in the universe, you could predict the future perfectly. Quantum mechanics says no. Heisenberg's uncertainty principle states that you cannot simultaneously know both the exact position and exact momentum of a particle. The more precisely you measure one, the less precisely you can know the other. This isn't a limitation of measurement technology. It's a fundamental property of nature. The uncertainty principle arises from wave-particle duality. A wave that's localized in space, well-defined position, must contain many different wavelengths, uncertain momentum. A wave with a well-defined wavelength, precise momentum, must be spread out in space, uncertain position. This has profound implications. It means the future is fundamentally unpredictable, even in principle. Quantum mechanics is probabilistic, not deterministic. Einstein hated this. He famously said, "God does not play dice with the universe." But experiments have proven him wrong. The universe does play dice. Quantum entanglement. Einstein called it spooky action at a distance, and it bothered him for the rest of his life. When two particles interact, they can become entangled. Their quantum states become correlated in ways that can't be explained by classical physics. Measure one particle, and you instantly know something about the other, even if they're on opposite sides of the universe. This seems to violate the principle that nothing can travel faster than light. How can measuring one particle instantly affect another particle light years away? Einstein, along with Boris Podolsky and Nathan Rosen, proposed that quantum mechanics must be incomplete. There must be hidden variables, properties that particles have all along, which quantum mechanics doesn't describe. In 1964, physicist John Bell devised a test to determine whether hidden variables exist. Bell's theorem showed that if hidden variables exist, certain statistical correlations between entangled particles would have an upper limit. Experiments have been performed many times with increasingly sophisticated setups. The results consistently violate Bell's inequalities. Hidden variables don't exist, or if they do, they must be non-local, allowing faster-than-light influences. Entanglement is real. Particles can be correlated in ways that seem to require instant communication across any distance. This doesn't allow faster-than-light communication, though. You can't control what result you get when you measure your particle, so you can't send information to the other particle. But it does mean that quantum mechanics is fundamentally non-local. The universe is more connected than classical physics suggests. The measurement problem. Here's the central mystery of quantum mechanics. What happens during measurement? Before measurement, a quantum system exists in a superposition of multiple states. The wave function describes the probability of finding the system in each state. When you measure it, you get one definite result. The wave function collapses from a superposition to a single state. But what causes this collapse? The equations of quantum mechanics don't describe it. They only describe how the wave function evolves smoothly over time. Measurement seems to be a special process, fundamentally different from normal quantum evolution. But what makes measurement special? Is it the interaction with a macroscopic measuring device, the involvement of consciousness, something else? This is the measurement problem, and it's been unsolved for a century. Interpretations of quantum mechanics. Because the measurement problem is unsolved, physicists have proposed various interpretations of what quantum mechanics means. The Copenhagen interpretation. This is the traditional view, developed by Niels Bohr and Werner Heisenberg. It says that the wave function represents our knowledge about a system, not the system itself. Measurement causes the wave function to collapse, giving a definite result. The Copenhagen interpretation doesn't explain what causes collapse or what constitutes a measurement. It essentially says, don't ask what's really happening. Just use the equations to make predictions. This pragmatic approach works for doing calculations, but it's philosophically unsatisfying. Many worlds interpretation. Proposed by Hugh Everett in 1957, this interpretation says there's no wave function collapse. Instead, every time a quantum measurement occurs, the universe splits into multiple branches. In one branch, you measure spin up. In another branch, you measure spin down. Both outcomes occur in different universes. From your perspective, you only see one outcome because you're in one branch, but all possible outcomes are equally real, occurring in parallel universes. This solves the measurement problem. There is no collapse, but at the cost of an infinite number of parallel universes. Is it true? We don't know. It makes the same predictions as other interpretations, so we can't test it directly. Pilot wave theory, de Broglie-Bohm. This interpretation, developed by Louis de Broglie and David Bohm, says that particles have definite positions at all times, guided by a pilot wave. The wave function is real and guides the particle's motion. There's no superposition of particle positions. The particle is always somewhere specific, but the pilot wave creates interference effects. This interpretation is deterministic and doesn't require wave function collapse, but it's non-local. The pilot wave depends on the entire configuration of all particles and seems to require a preferred reference frame. Objective collapse. Theories. These theories propose that wave function collapse is a real physical process, triggered when a system reaches a certain size or complexity. The Gherardi-Rimini-Weber (GRW) theory and Penrose's gravitational collapse theory are examples. These theories modify quantum mechanics slightly, predicting tiny deviations from standard quantum mechanics that might be testable with sufficiently sensitive experiments. So far, no deviations have been found. Which interpretation is correct? We don't know. All interpretations make the same predictions for experiments we can currently perform. This is frustrating. We have a theory that works perfectly for making predictions, but we don't know what it means. It's like having a car that runs perfectly, but not knowing whether it has an engine or is pushed by invisible gnomes. Dardis, quantum tunneling in. Classical physics. If you don't have enough energy to climb over a barrier, you can't get to the other side. In quantum mechanics, you can tunnel through. A particle's wave function extends into regions that are classically forbidden. There's a small probability that the particle will be found on the other side of a barrier, even if it doesn't have enough energy to go over it. This isn't just theoretical. Quantum tunneling is essential for nuclear fusion in stars, including our Sun, radioactive decay, scanning tunneling microscopes, flash memory in computers. Without quantum tunneling, the Sun wouldn't shine, and modern technology wouldn't exist. Quantum computing. Quantum mechanics isn't just philosophically interesting, it's technologically revolutionary. A classical computer stores information in bits, each either 0 or 1. A quantum computer uses qubits, which can be in a superposition of 0 and 1 simultaneously. With n qubits, a quantum computer can be in a superposition of 2 Lannon states at once. This allows certain calculations to be performed exponentially faster than on classical computers. Quantum computers could factor large numbers, breaking current encryption, simulate quantum systems, designing new materials and drugs, optimize complex systems, search databases faster. Building practical quantum computers is incredibly difficult. Qubits are fragile and easily disrupted by their environment, a process called decoherence. Maintaining quantum superposition requires extreme isolation and cooling, but progress is rapid. Companies like IBM, Google, and others have built quantum computers with dozens of qubits. In 2019, Google claimed quantum supremacy, performing a calculation that would be impractical for classical computers. We're at the beginning of a quantum revolution. Quantum teleportation. Despite the name, this doesn't involve transporting matter. Quantum teleportation transfers the quantum state of one particle to another distant particle using entanglement. Here's how it works. 1. Create two entangled particles, A and B. 2. Send particle B to a distant location. 3. Interact particle A with the particle whose state you want to teleport. 4. Measure both particles. 5. Send the measurement results, classical information, to the distant location. 6. Use that information to manipulate particle B, giving it the same state as the original particle. The original particle's state is destroyed in the process. You can't clone quantum states, but the state is recreated at the distant location. This has been demonstrated in laboratories with photons, atoms, and even small molecules. It might enable quantum communication networks and quantum internet. True, the quantum vacuum. In quantum field theory, even empty space isn't truly empty. The vacuum is seething with virtual particles, particle-antiparticle pairs that pop into existence and annihilate almost instantly, borrowing energy from the vacuum for brief moments allowed by the uncertainty principle. This isn't just theoretical. The Casimir effect demonstrates it. Two metal plates placed very close together in a vacuum experience an attractive force because certain virtual particles can't fit between the plates, creating a pressure difference. The vacuum energy has real measurable effects. But as we discussed in the dark energy chapter, the calculated vacuum energy is 10^120 times larger than what we observe. This is the cosmological constant problem, one of the deepest mysteries in physics. Quantum biology. Quantum effects aren't limited to physics labs and computers. They might play a role in biology. Photosynthesis. Plants might use quantum coherence to transfer energy with near-perfect efficiency. Bird navigation. Some birds might use quantum entanglement in their eyes to sense Earth's magnetic field. Enzyme catalysis. Quantum tunneling might enable certain biochemical reactions. Olfaction. Our sense of smell might involve quantum effects. These ideas are controversial and still being investigated. But if true, they'd mean that life itself exploits quantum mechanics. We might be quantum beings, our very existence depending on the strange rules of the quantum realm. The quantum classical boundary. One of the biggest unsolved questions. Why does the quantum world seem so different from the classical world we experience? Everyday objects don't exist in superpositions. Cats are either alive or dead, not both simultaneously, despite Schrödinger's famous thought experiment. Why not? The standard answer is decoherence. Large objects interact with their environment in countless ways, and these interactions destroy quantum superpositions almost instantly. But decoherence doesn't solve the measurement problem. It explains why we don't see macroscopic superpositions, but not why measurement gives definite results. Some physicists think there's a fundamental boundary between quantum and classical, perhaps related to gravity. Others think the quantum rules apply to everything, including us, but we can't perceive our own superpositions. We don't know where or why the quantum classical boundary exists. Living in a quantum universe. Quantum mechanics is the foundation of reality. Everything, atoms, molecules, light, matter, is fundamentally quantum. The classical world we experience is an approximation, an emergent phenomenon arising from quantum rules. This means reality is far stranger than it appears. Objects don't have definite properties until measured. The future is probabilistic, not deterministic. Particles can be entangled across vast distances. The vacuum isn't empty, but filled with quantum fluctuations. And we don't really understand why any of this is true. Quantum mechanics works. Its predictions have been confirmed to extraordinary precision. Every piece of modern technology relies on it, but we don't know what it means. This is science at its most profound. We have a theory that describes reality with perfect accuracy. Yet we can't agree on what it's telling us about the nature of existence. The quantum realm is waiting to reveal its deepest secrets, and those secrets might reshape our understanding of everything. What if our universe isn't the only one? What if there are countless other universes, each with different laws of physics, different constants of nature, different histories? What if every possible outcome of every quantum measurement occurs in some universe? What if there are infinite versions of you, making different choices, living different lives? This is the multiverse hypothesis, and it's one of the most controversial ideas in modern physics. It sounds like science fiction, but it emerges naturally from several well-established theories. The multiverse might not just be possible, it might be inevitable, or it might be untestable speculation that's led physics astray. The debate continues. Types of multiverses. Physicist Max Tegmark proposed a classification of 4 levels of multiverse. Level 1, beyond our cosmic horizon. This is the simplest multiverse and it's almost certainly real. The observable universe is finite. We can only see about 93 billion light-years in any direction, limited by the speed of light and the age of the universe. But the universe itself might be infinite. If so, there's more universe beyond our cosmic horizon, regions we can never observe because their light hasn't had time to reach us. In an infinite universe, every possible arrangement of matter must occur somewhere. There would be infinite copies of Earth, infinite versions of you, living out every possible variation of your life. This seems bizarre, but it's a logical consequence of infinity. If space is infinite and matter is distributed roughly uniformly, then any finite configuration, like the arrangement of atoms in your body, must repeat infinitely many times. The nearest identical copy of you might be 1010 on 29 meters away. That's a number so large it's meaningless, but in an infinite universe, it exists. Level 2. Bubble universes from inflation. Cosmic inflation, the rapid expansion of the universe in its first fraction of a second, is our best explanation for several features of the cosmos. But inflation might not have ended everywhere at once. In eternal inflation models, inflation stops in some regions, creating bubble universes like ours, but continues in others. New bubbles constantly form, each becoming a separate universe with its own Big Bang. These bubble universes would be forever beyond our reach, separated by regions of space that are still inflating. Different bubbles might have different physical constants. The strength of gravity, the mass of the electron, the number of dimensions, all could vary from bubble to bubble. Most bubbles would be sterile, unable to support complex structures. But in the infinite ensemble, some bubbles would have just the right properties for stars, planets, and life. We find ourselves in one of those rare bubbles, not because it's special, but because it's the only type where observers can exist. Level 3. Many worlds, quantum multiverse. As discussed in the quantum mechanics chapter, the many worlds interpretation says that every quantum measurement causes the universe to split into multiple branches. Measure an electron's spin. The universe splits into one branch where you measured spin up and another where you measured spin down. Both outcomes are real, occurring in parallel universes. This happens constantly with every quantum interaction. The number of parallel universes is unimaginably vast and growing exponentially. In some branch of the multiverse, you made different choices. In some branch, you're a famous musician. In another, you never existed because your parents never met. Every possible quantum outcome occurs in some branch. This interpretation is mathematically elegant and solves the measurement problem, but it requires accepting an infinity of parallel realities. Level 4. Mathematical universe, hypothesis. This is the most radical proposal. Tegmark suggests that every mathematically consistent structure exists as a physical universe. The universe isn't just described by mathematics, it is mathematics. If this is true, then there are universes with different numbers of dimensions, different mathematical structures, even different logical rules. This level of multiverse would encompass all possible realities, limited only by mathematical consistency. It's deeply speculative, and most physicists are skeptical. But it's a fascinating idea that mathematics isn't just a tool for describing reality, but is reality itself. Evidence for the multiverse. Can we test the multiverse hypothesis? For level 1, infinite space, we might look for patterns in the cosmic microwave background that suggest the universe is finite or infinite. Current data is consistent with a flat, possibly infinite universe, but we can't be certain. For level 2, bubble universes, we might find evidence in the CMB of collisions between our bubble and others during the early universe. Some researchers have claimed to find such evidence, but it's controversial and not widely accepted. For level 3, many worlds, the interpretation makes the same predictions as standard quantum mechanics, so it's not directly testable. However, it might make different predictions for quantum gravity or cosmology. For level 4, mathematical structures, it's hard to see how we could test it. By definition, we can only observe our own mathematical structure. The lack of testability bothers many scientists. If a hypothesis can't be tested, is it science or philosophy? The fine-tuning problem. One of the strongest arguments for the multiverse comes from fine-tuning. The fundamental constants of nature, the strength of gravity, the mass of Tadidiar, the electron, the cosmological constant, appear to be precisely tuned for the existence of complex structures. Change any of these constants by even a small amount, and the universe would be radically different. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If gravity were slightly weaker, stars and galaxies might never form. If the strong nuclear force were slightly different, atomic nuclei couldn't exist. If the electromagnetic force were different, chemistry would be impossible. If the cosmological constant were much larger, the universe would have expanded too rapidly for galaxies to form. The list goes on. There are dozens of apparent coincidences, each necessary for our existence. Why are the constants so precisely tuned? 3 possible answers. 1. Necessity. The constants must have these values due to some deeper theory we haven't discovered. Yet 2. Design. An intelligent creator chose these values. 3. Anthropic selection. In a multiverse with varying constants, we necessarily find ourselves in a universe that allows observers. The multiverse provides a natural explanation for fine-tuning without invoking design. If there are countless universes with different constants, it's not surprising that we find ourselves in one of the rare universes that supports life. This is the anthropic principle. We observe what we observe because we exist. Universes that don't support observers have no one to observe them. The anthropic principle. The anthropic principle comes in 2 forms. Weak anthropic principle. We observe the universe to have properties that allow our existence, because if it didn't have those properties, we wouldn't be here to observe it. This is a tautology, but it's a useful one. It explains why we find ourselves in a universe with the right properties for life without requiring those properties to be likely or special. Strong anthropic principle. The universe must have properties that allow observers to exist at some point. This is more controversial. It seems to imply that the universe has a purpose or that observers are somehow necessary. Most physicists accept the weak anthropic principle as a valid selection effect. The strong version is more contentious. Criticisms of the multiverse. Not everyone accepts the multiverse hypothesis. Critics argue, lack of testability. If other universes are forever beyond our observation, how can we test the hypothesis? Without testability, is it science? Proponents respond that the multiverse might make testable predictions. For example, eternal inflation predicts certain patterns in the CMB. The multiverse might also predict that we should find ourselves in a typical universe among those that support observers, which could be tested. Occam's razor. Occam's razor says we should prefer simpler explanations. The multiverse seems to multiply entities beyond necessity. Why accept infinite universes when one will do? Proponents respond that the multiverse might actually be simpler. Eternal inflation is a simpler theory than inflation that somehow stops everywhere at once. Many worlds is simpler than Copenhagen interpretation with its ad hoc collapse postulate. The multiverse might be the simplest explanation, even if it seems extravagant. Giving up on explanation. Some critics argue that invoking the multiverse is giving up on finding deeper explanations. Instead of asking why the constants have the values they do, we just say, because we happen to be in a universe where they do. This seems unsatisfying. Science should explain, not just catalog possibilities. Proponents respond that if the multiverse is real, then the anthropic explanation is the correct one. We shouldn't reject a true explanation just because we find it unsatisfying. The measure problem. If there are infinite universes, how do we calculate probabilities? In an infinite multiverse, everything that can happen does happen infinitely many times. How do we make predictions? This is called the measure problem, and it's a serious challenge for multiverse theories. For example, in eternal inflation, some types of bubble universes are more common than others. But more common is tricky when both types are infinite. Various measures have been proposed, ways of assigning probabilities to different types of universes, but there's no consensus on which is correct. Without a solution to the measure problem, the multiverse might not make testable predictions after all. Simulated universes. Here's a disturbing possibility. We might be living in a computer simulation. If it's possible to simulate conscious beings, and there's no obvious reason it shouldn't be, then advanced civilizations might create many such simulations. If simulations are possible and common, then there would be far more simulated universes than real ones. Statistically, we're more likely to be in a simulation than in the base reality. This is the simulation argument proposed by philosopher Nick Bostrom. It's not a scientific theory. We have no evidence for or against it, but it's a logical possibility that's hard to dismiss. If we are in a simulation, the laws of physics might just be the rules of the simulation. The universe might be fundamentally computational. Could we test this? Perhaps. We might look for glitches, limitations in the simulation's resolution, or evidence of optimization for computational efficiency. Some physicists have suggested that the lattice structure of spacetime at the Planck scale might be evidence of a discrete computational universe, but this is highly speculative. The Boltzmann brain problem. Here's a paradox that arises in certain multiverse scenarios. In an infinite universe or multiverse, random quantum fluctuations can create anything given enough time. A fluctuation could create a functioning brain, complete with false memories, that exists for a brief moment before dissipating. Such Boltzmann brains would vastly outnumber evolved brains like ours because they require much less structure, just a brain, not an entire planet and ecosystem. If Boltzmann brains are more common than evolved observers, then you're more likely to be a Boltzmann brain than a real person. But Boltzmann brains have random, unreliable memories and perceptions. If you're probably a Boltzmann brain, you can't trust your observations or reasoning. This leads to a paradox. The theory predicts you can't trust the theory. Cosmologists take this problem seriously. A viable cosmological theory must predict that we're not Boltzmann brains. This constrains multiverse models and has implications for the far future of the universe. Diverse parallel lives. If the multiverse is real, there are profound implications for identity and existence. In the many worlds interpretation, there are countless versions of you, diverging with every quantum event. Are they you? Do you have moral obligations to your other selves? If you make a risky decision, you might die in some branches and survive in others. From a multiverse perspective, you're guaranteed to survive in some branches, the quantum suicide thought experiment. But this doesn't mean you should take risks. The versions of you that die are still real, and their suffering matters. The multiverse raises deep questions about personal identity, free will, and the nature of existence. The ultimate ensemble. If the level 4 multiverse is real, if every mathematical structure exists, then reality is far vaster than we can imagine. There would be universes with different numbers of dimensions, different particles, different forces, even different mathematical rules. Some would be simple, others incomprehensibly complex. Most would be sterile, unable to support observers. But in the infinite ensemble, some would have the right properties for life and consciousness. We find ourselves in one of those rare universes, not because it's special, but because it's the only type where we can exist. This is the ultimate anthropic explanation. The universe seems designed for us because we can only exist in a universe that seems designed for us. Living in a multiverse. If the multiverse is real, does it change anything? For practical purposes, no. We can only observe and interact with our own universe. The existence of other universes doesn't affect our daily lives, but philosophically, it changes everything. It means we're not just small in space and time, we're small in the space of all possible realities. It means the universe's apparent fine-tuning isn't a miracle or a mystery. It's a selection effect. It means that somewhere in the multiverse, every possible story is being lived out. And it means that the question, why does the universe exist, might have a simple answer. Because all possible universes exist. The unanswered questions. The multiverse. Hypothesis raises as many questions as it answers. Is the multiverse real, or is it untestable speculation? If it's real, which levels exist? Can we ever find evidence for other universes? How do we calculate probabilities in an infinite multiverse? What does the multiverse mean for personal identity and free will? We don't have answers yet. The multiverse might be the greatest discovery in the history of science, a revelation that reality is infinitely vaster than we imagined. Or it might be a dead end, a seductive idea that led physics astray. Time will tell. Time is the most familiar and most mysterious aspect of reality. We experience it constantly. We remember the past, exist in the present, and anticipate the future. Time flows, carrying us from birth to death, from cause to effect, from order to entropy. But what is time? Is it a fundamental feature of the universe or an illusion created by our consciousness? Does it flow, or is that just how we perceive it? Is the future already determined, or does it come into being moment by moment? Physics has revealed that time is far stranger than common sense suggests. It's not absolute or universal. It can slow down, speed up, and possibly even loop back on itself. And yet, despite a century of studying time through relativity and quantum mechanics, we still don't understand its most basic properties. Why does time flow in only one direction? Why can we remember the past but not the future? Why does time exist at all? These questions remain unanswered. Time in physics. In Newton's physics, time is absolute. It flows uniformly throughout the universe, the same for everyone everywhere. There's a universal now that everyone can agree on. Einstein shattered this picture. Special relativity revealed that time is relative. Two observers moving at different speeds will disagree about the duration of events and even about which events are simultaneous. There's no universal now. Simultaneity depends on your reference frame. If you travel at high speed and then return, less time will have passed for you than for those who stayed behind. This is time dilation, and it's been confirmed countless times with atomic clocks on airplanes and satellites. General relativity went further, showing that gravity slows time. Clocks run slower in stronger gravitational fields. Near a black hole, time slows dramatically. At the event horizon, time appears to stop from an outside perspective. Time is not separate from space. They're woven together into space-time, a four-dimensional fabric that can bend, stretch, and warp. In this picture, time is a dimension, similar to the three dimensions of space. The past, present, and future all exist equally in the block universe. The flow of time is an illusion created by our consciousness, moving through this static four-dimensional structure. But this raises profound questions. If the future already exists, is free will an illusion? If the past still exists, why can't we access it? The arrow of time. Here's a puzzle. The fundamental laws of physics are time-symmetric. They work equally well forward or backward in time. If you filmed a collision between two billiard balls and played it backward, the reversed motion would still obey Newton's laws. The same is true for quantum mechanics and relativity. The equations don't distinguish between past and future. And yet, time clearly has a direction. We age, we don't get younger. Eggs break, they don't spontaneously reassemble. Heat flows from hot to cold, never the reverse. This asymmetry is called the arrow of time, and it's one of the deepest mysteries in physics. The arrow of time is intimately connected to entropy, a measure of disorder or randomness. The second law of thermodynamics states that entropy always increases in a closed system. Order becomes disorder. Structure breaks down. The universe tends toward maximum entropy. This gives time a direction, toward increasing entropy. But why? If the fundamental laws are time-symmetric, why does entropy increase in one direction but not the other? The answer seems to be initial conditions. The universe started in an extremely low entropy state, the Big Bang, and it's been increasing in entropy ever since. But this just pushes the question back. Why did the universe start with low entropy? We don't know. The beginning of time. Did time have a beginning? According to the Big Bang theory, the universe began 13.8 billion years ago. Space, time, matter, and energy all came into existence at that moment. Before the Big Bang, there was no before. Time itself began with the universe. This is hard to wrap our minds around. We're used to thinking of time as eternal, extending infinitely into the past and future. But general relativity allows for time to have a beginning. At the Big Bang singularity, the equations break down, and time emerges from nothing, something else. Some theories propose that time is emergent. It arises from more fundamental timeless physics. In quantum gravity theories, space-time might be built from more basic entities that don't have temporal properties. Time would be an approximation, valid only at large scales. If this is true, then asking what happened before the Big Bang is like asking what's north of the North Pole. The question doesn't make sense because time itself didn't exist. Other theories propose that time is eternal, that the Big Bang was not the beginning, but a transition from a previous state. The universe might undergo cycles of expansion and contraction with no ultimate beginning or end. We don't know which picture is correct. The end of time. Will time have an end? If the universe expands forever, as current evidence suggests, time will continue indefinitely. But the universe will approach a state of maximum entropy, the heat death, where nothing interesting can happen. In this far future, all stars will have burned out, all black holes will have evaporated, and the universe will be a cold, dark, uniform sea of particles. Time will still exist, but nothing will change. Without change, does time have meaning? Some physicists argue that in a maximum entropy state, time effectively ends. There's no arrow of time because there's no entropy gradient. Other scenarios are possible. Big Rip. If dark energy grows stronger, it could tear apart all structures, including atoms, in a finite time. Big Crunch. If the universe's expansion reverses, it could collapse back to a singularity, ending time. Vacuum decay. The universe might be in a metastable state that could suddenly transition to a lower energy state, destroying everything. We don't know the ultimate fate of the universe, and thus we don't know if time will end. Time travel to the future. Time travel to the future is not only possible, it's easy. Just move fast or go near a strong gravitational field. If you travel at 99.9% the speed of light for what feels like 1 year to you, about 22 years will pass on Earth. You'll have traveled 21 years into the future. This is time dilation, a confirmed prediction of special relativity. Astronauts on the International Space Station age slightly slower than people on Earth, a few milliseconds over months. GPS satellites have to account for time dilation, or they'd quickly become inaccurate. In principle, you could travel arbitrarily far into the future. Travel close enough to the speed of light, and thousands or millions of years could pass on Earth while only a few years pass for you. The limitation is practical, not theoretical. Accelerating to such speeds requires enormous energy, but there's no law of physics preventing it. Chati. Time travel to the past. Time travel to the past is far more problematic. General relativity allows for solutions that include closed time-like curves, paths through spacetime that loop back on themselves, allowing you to return to your own past. These solutions require exotic conditions: rotating black holes, Kerr black holes, traversable wormholes, infinitely long rotating cylinders, Tipler cylinders, Alcubierre warp drives. All of these require either exotic matter with negative energy density or infinite structures. We've never observed such things, and they might be impossible. Even if they're possible, time travel to the past raises paradoxes. Lavrier's The Grandfather. Paradox. If you travel back in time and prevent your grandfather from meeting your grandmother, you would never be born. But if you're never born, you can't travel back in time to prevent their meeting. Paradox. Several solutions have been proposed. Yadlapar. Self-consistency. Perhaps the universe conspires to prevent paradoxes. You can travel to the past, but you can't change it. Every attempt to alter history fails in some way. This preserves logical consistency but seems to require a strange form of cosmic censorship. Many worlds. When you travel to the past, you create a new timeline. In this timeline, you prevent your grandparents from meeting, but this doesn't affect your original timeline. You're not changing the past, you're creating an alternate past in a parallel universe. This avoids paradoxes but requires the many worlds interpretation of quantum mechanics. Chronology protection. Stephen Hawking proposed the chronology protection conjecture. The laws of physics prevent time travel to the past, even if general relativity seems to allow it. Perhaps quantum effects destroy closed time-like curves, or perhaps there's a deeper principle we haven't discovered. We don't know if time travel to the past is possible. Most physicists are skeptical, but we can't rule it out entirely. The nature of now. What is the present moment? In relativity, there's no universal now. Different observers have different presents. Events that are simultaneous for one observer occur at different times for another. This suggests that the present isn't fundamental, it's observer-dependent. But our experience of time is centered on the present. The past is memory, the future is anticipation, but the present is real and immediate. How do we reconcile this with physics? One possibility is that consciousness creates the present. The now is a feature of how our brains process information, not a feature of the universe itself. Another possibility is that the present is the boundary between the determined past and the undetermined future. Quantum mechanics is probabilistic, so perhaps the future doesn't exist until quantum events collapse into definite outcomes. The present would be the moment of collapse, the transition from possibility to actuality. But this requires a solution to the measurement problem, which we don't have. The block universe. In the block universe view, all of space-time exists as a single unchanging four-dimensional structure. The past, present, and future are all equally real. They're just different regions of the block. Your entire life, from birth to death, exists as a four-dimensional world line through the block. From a timeless perspective, your entire history is laid out at once. The flow of time is an illusion. What we call now is just our consciousness moving along our world line, experiencing one moment after another. This view is suggested by relativity, which treats time as a dimension similar to space. But it's deeply counterintuitive. It implies that the future already exists, that everything that will happen has already happened from a timeless perspective. Does this mean free will is an illusion? If the future already exists, are our choices predetermined? Not necessarily. Even in a block universe, your choices are part of the structure. The future exists, but it exists as a consequence of your choices. It's a subtle distinction, and philosophers still debate whether the block universe is compatible with free will. Presentism versus eternalism. Presentism is the view that only the present exists. The past no longer exists, and the future doesn't exist yet. Eternalism is the view that past, present, and future all exist equally, the block universe. Relativity seems to favor eternalism. If simultaneity is relative, it's hard to define a universal present, but quantum mechanics might favor presentism. If the future is probabilistic and only becomes definite through measurement, then perhaps only the present and past are real. Reconciling these views is one of the challenges of developing a theory of quantum gravity. Time and consciousness. Why do we experience time as flowing? The laws of physics don't include a flow. They describe a static four-dimensional structure. Perhaps the flow of time is created by consciousness. Our brains process information sequentially, creating the illusion of time passing. Memory also plays a role. We remember the past but not the future, which creates an asymmetry in our experience of time. But why do we remember the past and not the future? This is connected to the arrow of time and entropy. Memories are low-entropy structures. Creating a memory requires increasing entropy elsewhere. The arrow of time, the direction of increasing entropy, determines the direction of causation and memory. If entropy were decreasing, we'd remember the future and not the past. Time would seem to flow backward, but this just pushes the question back. Why does entropy increase in one direction? None. The illusion of time. Some physicists argue that time is an illusion, a useful concept for describing change, but not a fundamental feature of reality. In quantum gravity theories, space-time might emerge from more basic, timeless entities. Carlo Rovelli, a proponent of loop quantum gravity, argues that time doesn't exist at the fundamental level. It emerges as an approximation when we consider large numbers of particles. Julian Barber goes further, proposing that each moment is a separate, timeless configuration. The appearance of time comes from correlations between these configurations. In this view, the universe is a vast collection of nows with no fundamental ordering or flow. These ideas are speculative, but they're taken seriously by physicists working on quantum gravity. Living in time. Whether time is fundamental or emergent, real or illusory, we experience it as the most basic feature of existence. We're temporal beings, born into a world where the past is fixed and the future is open. We make choices, we remember, we anticipate, we age, we change, we die. Time gives life meaning. Without time, there would be no growth, no learning, no stories. And yet, we don't understand it. We don't know why time has a direction, why it began, whether it will end, or even if it's real. Time is the ultimate mystery, the framework within which all other mysteries unfold, and it's waiting to reveal its secrets. Where did the universe come from? Where is it going? These are the most profound questions humanity has ever asked. They're questions about existence itself, about why there is something rather than nothing. For most of human history, these questions belong to religion and philosophy. Science had nothing to say about the origin of everything. That changed in the 20th century. We now have a scientific creation story, the Big Bang, supported by overwhelming evidence. We can trace the universe's history back to its first fraction of a second. We can predict its future billions of years hence. But the deepest questions remain unanswered. What caused the Big Bang? What came before? Why does the universe exist at all? And what will be the ultimate fate of everything? The Big Bang. 13.8 billion years ago, the universe began, not as an explosion in space, but as an explosion of space itself. All of space, time, matter, and energy emerged from an infinitesimally small, infinitely dense point. In the first 10⁻43 seconds, the Planck time, the universe was so hot and dense that our physics breaks down. We can't describe what happened in this earliest moment. We'd need a theory of quantum gravity, which we don't have. But after the Planck time, we can trace the universe's evolution. 10 or 36 to 10 or 32 seconds, inflation. The universe underwent a period of exponential expansion, growing from subatomic size to perhaps the size of a grapefruit in a tiny fraction of a second. Inflation explains several features of the universe. Why it's so uniform, different regions were once in contact. Why it's so flat, expansion stretched out any curvature. Why we don't see magnetic monopoles, they were diluted by expansion. Inflation also created the seeds of all future structure. Quantum fluctuations during inflation were stretched to cosmic scales, becoming the density variations that eventually grew into galaxies and galaxy clusters. 10, 12 seconds. Electroweak symmetry breaking. The electromagnetic and weak nuclear forces, which were unified at higher energies, separated into distinct forces. 10.6 seconds. Quark-gluon plasma. The universe was still too hot for protons and neutrons to form. Quarks and gluons existed in a hot plasma. 1 second. Neutrino decoupling. The universe cooled enough that neutrinos stopped interacting with other matter. These neutrinos still fill the universe today as the cosmic neutrino background, which we haven't yet detected directly. 3 minutes, Big Bang nucleosynthesis. Protons and neutrons combined to form the first atomic nuclei, hydrogen, helium, and trace amounts of lithium and beryllium. The ratios of these elements match observations precisely, providing strong evidence for the Big Bang. 80,000 years, recombination. The universe cooled enough for electrons to combine with nuclei, forming neutral atoms. Light could finally travel freely through space. This light, stretched and cooled by billions of years of expansion, is the cosmic microwave background, CMB, we observe today. 200 million years, first stars. Gravity pulled matter together, forming the first stars. These were massive, short-lived stars made entirely of hydrogen and helium. When they exploded as supernovae, they created and dispersed heavier elements, enriching the universe with the building blocks of planets and life. 1 billion years. First galaxies. Galaxies formed as dark matter halos pulled in ordinary matter. Supermassive black holes formed at their centers. 9 billion years, solar system formation. Our sun and solar system formed from a cloud of gas and dust enriched by previous generations of stars. 13.8 billion years. Today, we exist, looking back at the universe's history, trying to understand our origins. Dinosaurs, evidence for the Big Bang. The Big Bang theory is supported by multiple independent lines of evidence. Line 1. Cosmic expansion. Galaxies are moving away from us, with more distant galaxies receding faster. This is exactly what we'd expect if space itself is expanding. 2. Cosmic microwave background. The CMB is the afterglow of the Big Bang, predicted by the theory and discovered in 1965. Its temperature, 2.7 Kelvin, and spectrum match theoretical predictions perfectly. 3. Abundance of light elements. The ratios of hydrogen, helium, and lithium in the universe match the predictions of Big Bang nucleosynthesis. 4. Evolution of galaxies. Distant galaxies, which we see as they were in the past, look different from nearby galaxies, showing that the universe has evolved over time. 5. Distribution of large-scale structure. The pattern of galaxy clusters and voids matches predictions from simulations, starting with Big Bang initial conditions. No alternative theory explains all these observations as well as the Big Bang. What came before? The Big Bang theory describes the universe's evolution from an early hot, dense state, but it doesn't explain what caused that state or what came before. Several possibilities have been proposed. Sakura's Ra. Quantum creation from nothing. In quantum mechanics, particles can spontaneously appear from the vacuum. Perhaps the entire universe appeared this way, a quantum fluctuation that grew into everything we see. Physicist Alexander Vilenkin proposed that the universe tunneled into existence from nothing using quantum mechanics. But what does nothing mean? Even the quantum vacuum has properties and follows laws. Where did those come from? Eternal inflation. In eternal inflation models, our Big Bang was just one bubble in an eternally inflating multiverse. Inflation never ends globally. It only ends in local regions, creating bubble universes. This pushes the question back. What started inflation? Did it have a beginning, or is it eternal? Cyclic universe. Perhaps the universe undergoes endless cycles of expansion and contraction. The Big Bang was not the beginning, but a transition from a previous contracting phase. In some cyclic models, the universe bounces at a minimum size, avoiding a singularity. In others, the universe passes through a singularity, with information from the previous cycle lost. These models face challenges, particularly from entropy. Each cycle should have higher entropy than the last, but we observe a low-entropy universe. Where did the low entropy come from? Quantum gravity. Perhaps the question, what came before the Big Bang, doesn't make sense because time itself is emergent. In quantum gravity theories, spacetime might not be fundamental. It might emerge from more basic timeless entities. If time emerges with the universe, there is no before. We don't have a complete theory of quantum gravity yet, so this remains speculative. The flatness problem. Measurements show that the universe is spatially flat, or very close to it. This means that parallel lines remain parallel forever, and the angles of a triangle add up to 180 degrees. But flatness is unstable. Any small deviation from flatness in the early universe would have grown rapidly. For the universe to be as flat as we observe today, it must have been extraordinarily flat in the beginning, fine-tuned to 1 part in 10^60. Why? Inflation provides an answer. Exponential expansion stretches out any curvature, making the universe flat regardless of its initial state. But this just pushes the question back. What caused inflation? The horizon problem. The CMB is remarkably uniform. Its temperature is the same in all directions to 1 part in 100,000. This is puzzling because regions of the CMB that are on opposite sides of the sky have never been in contact. They're too far apart for light to have traveled between them in the age of the universe. How did they reach the same temperature? Again, inflation provides an answer. Before inflation, these regions were close together and in thermal equilibrium. Inflation then stretched them apart faster than light could travel. The monopole problem. Grand unified theories predict that the early universe should have produced magnetic monopoles, particles with only a north or south magnetic pole. We've never observed magnetic monopoles, despite extensive searches. Inflation explains this. Monopoles were produced before inflation, but inflation diluted them to undetectable levels. The future. Heat death. If dark energy remains constant, as current evidence suggests, the universe will expand forever, accelerating eternally. Here's what will happen. 100 billion years from now, galaxies beyond our local group will have receded beyond the cosmic horizon. Future astronomers will see only the Milky Way, Andromeda merged galaxy, surrounded by darkness. 1 trillion years. Star formation will cease as galaxies run out of gas. The universe will grow darker. 100 trillion years. The last stars will die. The universe will be dominated by stellar remnants, white dwarfs, neutron stars, and black holes. 40 years. Protons may decay, if certain theories are correct, causing even white dwarfs and neutron stars to evaporate. 100 years. The largest black holes will evaporate through Hawking radiation. 10 to 20 years. The universe reaches maximum entropy. All energy is evenly distributed. No structure remains. Nothing interesting can ever happen again. This is the heat death, not a dramatic end, but a slow fade into cold, dark uniformity. Alternative fates. Other scenarios are possible, depending on the nature of dark energy. Big Rip. If dark energy grows stronger over time, phantom energy, the expansion will accelerate without limit. Eventually, the acceleration will become so strong that it tears apart. Galaxy clusters in 20 billion years, galaxies in 60 million years before the end, solar systems in 3 months before the end, planets in 30 minutes before the end, atoms in the final fraction of a second. The universe would end in violent disintegration. Big Crunch. If dark energy weakens or reverses, the universe's expansion could slow, stop, and reverse. The universe would collapse back on itself, growing hotter and denser, eventually reaching a big crunch, a reverse Big Bang. This could lead to a cyclic universe, with endless cycles of expansion and contraction. Current evidence suggests this won't happen, but we can't rule it out entirely. Vacuum decay. The universe might be in a metastable state, like a ball balanced on a hilltop, stable for now but vulnerable to collapse. If the universe's vacuum state is metastable, A quantum fluctuation could trigger a transition to a lower energy state. This would create a bubble of true vacuum, expanding at the speed of light, destroying everything in its path. The laws of physics inside the bubble would be different. Atoms couldn't exist. Everything would be annihilated. This could happen tomorrow or never. We have no way to predict it. If it happens, we won't see it coming. The bubble would arrive at the speed of light, giving no warning. The anthropic principle and the future. The anthropic principle applies not just to the universe's properties, but to its timing. We exist in an era when the universe is old enough for complex life to evolve, but young enough that stars still shine and galaxies are visible. In the far future, the universe will be dark and empty. Observers in that era, if any exist, won't be able to discover the Big Bang or cosmic expansion. They'll be cosmologically isolated. We're fortunate to live in an era when the universe reveals its secrets. The meaning of the end. The eventual heat death of the universe is often described as bleak or nihilistic. If everything ends in cold darkness, does anything matter? But this perspective misses something important. Meaning isn't about duration, it's about experience. A song doesn't become meaningless because it ends. A story isn't pointless because it has a final page. The universe will end, but that doesn't diminish the beauty of a sunset, the joy of discovery, the love between people. We exist in a brief, bright moment in cosmic history. That moment is precious precisely because it's temporary. The ultimate mystery. Despite all we've learned, the deepest question remains unanswered. Why is there something rather than nothing? Why does the universe exist at all? Some physicists argue that nothing is unstable, that quantum mechanics allows or requires something to emerge from nothing. Others propose that the universe is eternal, with no beginning and no need for a cause. Still others suggest that the question is meaningless, that asking why the universe exists is like asking what's north of the North Pole. And some argue that we may never know, that the origin of existence might be forever beyond scientific explanation. This is the ultimate mystery, the question at the foundation of all others, and it's still waiting for an answer. We began this journey standing under the stars, asking the oldest questions humanity has ever posed. What is the universe made of? How did it begin? Where is it going? Are we alone? What is the nature of reality itself? We've explored dark matter, the invisible scaffolding that holds galaxies together, making up 27% of the universe yet remaining undetected in our laboratories. We've confronted dark energy, the mysterious force accelerating cosmic expansion, comprising 68% of everything yet defying explanation. We've ventured to the edge of black holes, where space-time curves so severely that it creates one-way boundaries in reality, where our theories break down and new physics awaits. We've asked why, in a universe billions of years old and trillions of light-years across, we haven't encountered other intelligent civilizations, the great silence that might herald our uniqueness or warn of dangers ahead. We've descended into the quantum realm, where particles exist in superposition, where observation changes reality, where the universe seems to operate according to rules that defy common sense. We've considered the multiverse, the possibility that our universe is just one among countless others, each with different laws and constants, most sterile and lifeless, but some, like ours, capable of supporting observers. We've grappled with time, that mysterious dimension that flows in only one direction, that might be fundamental or might be an illusion, that began with the Big Bang and might end with heat death. And we've traced the universe from its fiery birth to its ultimate fate, from the first fraction of a second to the last black hole evaporating in the incomprehensibly distant future. Through it all, one theme has emerged. The more we learn, the more we realize how much we don't know. The limits of knowledge. Science has accomplished miracles. We've split the atom, decoded the genome, landed on the moon, and photographed the shadow of a black hole. We've discovered that the universe is 13.8 billion years old, that it's expanding and accelerating, that it began in a Big Bang and will likely end in heat death. We've found that reality is quantum, that space-time is curved, that matter and energy are equivalent. We've built technologies that would seem like magic to our ancestors: computers, smartphones, GPS, MRI machines, solar panels. And yet, fundamental mysteries remain. We don't know what dark matter is. We don't know what dark energy is. We don't know how to reconcile quantum mechanics with general relativity. We don't know if we're alone in the universe. We don't know if the multiverse is real. We don't know why time has an arrow. We don't know why the universe exists. These aren't minor gaps in our knowledge. They're fundamental questions about the nature of reality. Will we ever answer them? Maybe. Science has surprised us before, solving problems that seemed impossible. Or maybe some questions are beyond human comprehension. Maybe our brains, evolved to navigate an African savanna, simply aren't equipped to understand the deepest truths about reality. Or maybe the questions themselves are flawed, based on assumptions that will seem quaint to future generations. We don't know, and that's okay. The value of mystery. There's a tendency to view unsolved mysteries as failures, as problems that science hasn't yet fixed. But mysteries aren't failures, they're opportunities. Every unsolved problem is an invitation to discovery, a frontier where the next great breakthrough awaits. The mysteries we've explored in this script represent the cutting edge of human knowledge. They're where the most brilliant minds in physics are working, where the next Einstein or Hawking might make their mark. And mysteries have value beyond their solutions. They inspire wonder. They remind us that the universe is far stranger and more magnificent than our everyday experience suggests. They humble us, showing that despite all our progress, we're still at the beginning of understanding, and they unite us. The questions we've explored aren't American or Chinese, Christian or Muslim, capitalist or communist. They're human questions, asked by anyone who looks at the night sky and wonders. What we've learned about learning. This journey through cosmic mysteries has revealed something important about the nature of knowledge itself. Science is self-correcting. When new evidence contradicts a theory, the theory must change. Newton's laws were replaced by Einstein's relativity in extreme conditions. Our understanding of the universe's fate has changed as we've discovered dark energy. This isn't weakness, it's strength. Science doesn't claim absolute truth, only the best explanation given current evidence. Uncertainty is honest. When scientists say, "We don't know," that's not an admission of failure. It's an honest assessment of the evidence. Contrast this with dogma, which claims certainty without evidence. Science's willingness to embrace uncertainty is what makes it reliable. Mathematics is the language of nature. Again and again, we've found that the universe operates according to mathematical principles. General relativity is a set of equations. Quantum mechanics is a mathematical framework. The standard model of particle physics is a mathematical structure. Why mathematics describes reality so well is itself a mystery, one we haven't explored in depth. But it's a profound clue about the nature of the universe. Observation is supreme. No matter how elegant a theory, no matter how brilliant the physicist who proposed it, if it doesn't match observations, it's wrong. This is what separates science from philosophy. We don't just think about the universe, we test our ideas against reality. Collaboration accelerates discovery. The discoveries we've discussed weren't made by lone geniuses working in isolation. They emerged from collaboration, thousands of scientists sharing data, checking each other's work, building on each other's insights. The Event Horizon telescope that photographed a black hole involved over 200 scientists from around the world. The detection of gravitational waves required decades of work by thousands of people. Modern science is a collective endeavor, and that's its strength. The human element. Throughout this journey, we've focused on cosmic mysteries, vast impersonal forces and structures. But there's a human element to all of this. Every discovery we've discussed was made by people who were curious, who asked questions, who refused to accept easy answers. People like Vera Rubin, who persisted in studying galaxy rotation despite skepticism, eventually providing crucial evidence for dark matter. People like Saul Perlmutter, Brian Schmidt, and Adam Rees, who discovered cosmic acceleration even though it contradicted expectations. People like Stephen Hawking, who showed that black holes aren't entirely black, revolutionizing our understanding of quantum gravity. These weren't superhuman geniuses. They were people, smart and dedicated, yes, but people nonetheless. They made mistakes. They had doubts. They faced rejection and criticism, but they persisted. And that's the real lesson. Discovery is possible. Understanding is achievable. The universe's mysteries can be unraveled, one insight at a time. You don't need to be Einstein to contribute. You just need curiosity, rigor, and persistence. The next generation. The mysteries we've explored won't be solved by the current generation of physicists alone. Some will require new technologies, more sensitive dark matter detectors, more powerful telescopes, more advanced quantum computers. Some will require new theoretical frameworks, a theory of quantum gravity, a deeper understanding of the quantum measurement problem, a resolution to the cosmological constant problem. Some will require new ways of thinking, paradigm shifts as radical as relativity and quantum mechanics were a century ago. The next generation of scientists, perhaps including some reading this, will tackle these challenges. They'll have tools we can only dream of. Space-based gravitational wave detectors, quantum computers with millions of qubits, telescopes that can directly image exoplanet surfaces. They'll ask questions we haven't thought of yet, and they'll make discoveries that will seem as revolutionary to us as relativity seemed to Newton. The future of science is bright. The philosophical implications. The mysteries we've explored aren't just scientific, they're philosophical. What is real? Quantum mechanics suggests that reality depends on observation. The multiverse hypothesis suggests that all possible realities exist. Are we prepared to accept such radical revisions to our concept of reality? What is consciousness? The measurement problem in quantum mechanics raises questions about the role of observers. Is consciousness fundamental to physics, or is it an emergent phenomenon? What is our place in the universe? If we're alone, we're precious beyond measure. If we're not alone, we're part of something larger. Either answer is profound. What is the meaning of existence? If the universe will end in heat death, if everything we build will eventually decay, does anything matter? These questions don't have scientific answers. They're philosophical and personal. But science informs them. Our understanding of the universe shapes how we think about meaning, purpose, and value. The practical implications. These cosmic mysteries might seem abstract and disconnected from everyday life, but they have practical implications. Technology. Quantum mechanics, once a purely theoretical curiosity, now underlies all modern electronics. Quantum computers might revolutionize medicine, cryptography, and artificial intelligence. General relativity is essential for GPS. Without accounting for time dilation, GPS would be off by kilometers. Understanding dark matter and dark energy might lead to new technologies we can't yet imagine. Existential risk. The Fermi Paradox raises the possibility of a great filter, something that prevents civilizations from spreading across the galaxy. If the filter is ahead of us, we need to be very careful about existential risks: nuclear war, climate change, artificial intelligence, biotechnology. Understanding our cosmic context helps us assess these risks. Resources. The universe is vast and mostly empty, but it contains unimaginable resources. Asteroids contain metals worth quadrillions of dollars. The energy output of the sun dwarfs all human energy consumption. Understanding the universe is the first step toward utilizing its resources. Inspiration. Perhaps most importantly, cosmic mysteries inspire us. They remind us that there's more to life than our immediate concerns. They give us perspective, showing that we're part of something vast and ancient. They inspire young people to pursue science, to ask questions, to seek understanding. And they unite humanity around common goals: to explore, to discover, to understand. The ethics of discovery. As we pursue these mysteries, we face ethical questions. Should we send messages to extraterrestrial civilizations? The potential reward is contact with another intelligent species. The potential risk is attracting hostile attention. Who decides? Does humanity need to reach consensus before broadcasting our presence? Should we create artificial intelligence that might surpass human intelligence? AI could solve many of the mysteries we've discussed, but it could also pose existential risks. How do we balance the potential benefits against the risks? Should we pursue technologies that could destroy us? Particle accelerators, synthetic biology, nanotechnology all have potential benefits and risks. How do we proceed safely? How do we distribute the benefits of discovery? Scientific knowledge is a common heritage of humanity, but its applications often benefit some more than others. How do we ensure that discoveries serve all of humanity, not just the wealthy or powerful? These are difficult questions without easy answers, but they're questions we must grapple with as we continue to explore the universe's mysteries. Title: The Beauty of the Unknown. There's something beautiful about not knowing. If we understood everything, if every mystery were solved, what would be left to discover? The unknown is what makes science exciting. It's what drives exploration and discovery. Every answer raises new questions. Every solution reveals new mysteries. This isn't frustrating, it's wonderful. It means there will always be frontiers to explore, always new things to learn, always opportunities for wonder. The universe is under no obligation to make itself easy to understand. The fact that we can understand it at all, even partially, is a gift. A message to the future. If someone reads this script 100 years from now, what will they think? Perhaps they'll smile at our ignorance, the way we smile at 19th century scientists who didn't know about atoms or relativity. Perhaps they'll have detected dark matter, understood dark energy, found life on other worlds, built quantum computers that dwarf anything we can imagine. Perhaps they'll have answered questions we haven't even thought to ask. Or perhaps they'll still be grappling with the same mysteries, humbled by the universe's complexity. Either way, I hope they'll recognize that we were trying, that we were asking the right questions, even if we didn't have all the answers, that we were driven by curiosity and wonder, by a desire to understand our place in the cosmos, that we were, in our own small way, continuing humanity's greatest adventure, the quest to understand the universe and our place within it. A message to you. You've journeyed with me through some of the deepest mysteries in science. You've confronted ideas that challenge intuition, particles in superposition, space-time curvature, cosmic acceleration, parallel universes. You've grappled with questions that have no easy answers. Why does the universe exist? Are we alone? What is time? What is real? I hope you've emerged with a sense of wonder. The universe is far stranger, far more magnificent, far more mysterious than our ancestors ever imagined. We live in an age of discovery, when telescopes peer to the edge of the observable universe, when particle accelerators recreate conditions from the first moments after the Big Bang, when we can photograph black holes and detect gravitational waves. We're privileged to live in a time when the universe reveals its secrets, but we're also humbled by how much remains unknown. The invitation. This script is an invitation to wonder, to question, to explore, an invitation to look at the night sky and see not just pretty lights, but galaxies billions of light years away, each containing hundreds of billions of stars. An invitation to recognize that you're made of atoms forged in the hearts of dying stars, that you're the universe become conscious of itself. An invitation to embrace mystery, to be comfortable with uncertainty, to find beauty in the unknown. An invitation to participate in humanity's greatest adventure, the quest to understand the cosmos. You don't need a PhD to appreciate these mysteries. You don't need to understand the mathematics. You just need curiosity and a willingness to have your mind expanded. The universe is waiting. The final mystery. We've explored 10 chapters of cosmic mysteries, from dark matter to the multiverse, from black holes to the nature of time. But there's one final mystery we haven't addressed. Why is the universe comprehensible? Why can we, tiny beings on a small planet, understand the laws that govern galaxies and atoms? Why does mathematics, a product of human minds, describe reality with such precision? Why is the universe not just orderly, but understandable? This is perhaps the deepest mystery of all. Einstein called it the most incomprehensible thing about the universe. We don't have an answer, but the fact that we can ask the question, that we can understand so much, is itself a kind of miracle. Embracing the Unknown. The title of this chapter is Embracing the Unknown, and that's the ultimate lesson of our journey. We don't have all the answers. We might never have all the answers, and that's okay. The unknown isn't something to fear. It's something to celebrate. It's where discovery happens. It's where wonder lives. It's what makes the universe endlessly fascinating. So embrace the mystery. Ask questions. Seek understanding. But also, appreciate the beauty of not knowing, the thrill of exploration, the joy of discovery. The universe is vast and ancient and strange, and it's waiting for you to explore it. The end and the beginning. This script has come to an end, but your journey is just beginning. The mysteries we've explored are real. They're being investigated right now by scientists around the world. Some will be solved in your lifetime. You might read a headline tomorrow. Dark matter detected, or life found on Europa, or quantum gravity theory confirmed. Each discovery will answer old questions and raise new ones, and you'll be there to witness it. You'll see humanity take its next steps in understanding the cosmos. You'll see the universe reveal more of its secrets. And perhaps, if you're inspired by these mysteries, you'll contribute to that understanding. Perhaps you'll be the one to detect dark matter, or discover life on another world, or solve the measurement problem in quantum mechanics. Or perhaps you'll simply look at the night sky with new eyes, seeing not just stars, but the vast, mysterious, magnificent universe in all its complexity. Either way, you'll be part of the story. The story of humanity's quest to understand the cosmos. The story that began when the first human looked at the stars and wondered. The story that continues today with telescopes and particle accelerators and brilliant minds asking profound questions. The story that will continue long after we're gone, as future generations push the boundaries of knowledge ever further. It's the greatest story ever told, and you're part of it. The universe awaits. We began this journey with a simple question: where is everybody? We end with a simple truth: the universe is waiting, waiting to be explored, waiting to be understood, waiting to reveal its deepest secrets. The mysteries we've discussed, dark matter, dark energy, black holes, the Fermi Paradox, quantum mechanics, the multiverse, time, the origin and fate of everything, these are the frontiers of human knowledge. There where the next great discoveries will be made. There where the future of science lies, and they're accessible to anyone with curiosity and wonder. So go outside tonight. Look at the stars. Remember that the darkness between them is filled with invisible dark matter and dark energy. Remember that some of those stars might have planets harboring life. Remember that the light you're seeing left those stars years or centuries or millennia ago. Remember that you're looking back in time, witnessing the past. Remember that you're made of atoms forged in stars that died before the sun was born. Remember that you're the universe become conscious of itself. And remember that despite all we've learned, despite all our progress, the universe still holds mysteries beyond our current understanding. Those mysteries are waiting. For you. For all of us. For anyone brave enough to ask, why? The universe is vast and ancient and strange and beautiful, and it's yours to explore.